Understanding the models that power agents is crucial because their capabilities and optimization strategies directly influence how effectively these agents perform tasks. We'll explore what these models are, how they work, and the techniques used to improve their performance. Selecting the right model family is crucial for agent workloads because it impacts performance, efficiency, and cost. Different model architectures offer various strengths, so understanding these differences helps match the model to the task requirements effectively. Choosing a model for an agent system is not just about picking the one with the best score. Instead, it involves understanding how the model fits into a dynamic decision-making process within the system. A high benchmark score only shows that a model performs well on a specific task under fixed conditions. But an agent's workload is a sequence of decisions where each choice affects the next. The model must work within a loop, adapting as the situation changes, not just produce a single good answer. In an agent, the model is part of a system that controls when it acts and how it interacts with other components. Its output can be more than text. It might be a command or a state update. A model that excels in one-off tests can struggle in repeated, stateful interactions, while a less flashy model might be better suited for consistent, reliable performance in the agent's loop. It's important to consider what repeated decisions the system needs to support. The model should maintain intent across turns and operate within defined action limits. It must stay useful even when external tools or other agents change the task state. This shifts focus from abstract quality to practical fit for the system's workflow. This figure illustrates how model choice differs in an agent system. The model participates in a loop where each action changes the state and affects what happens next, rather than providing a single isolated response, as in traditional benchmarks. Think of an agent system like a team where each member has a specific role suited to their skills. One model might handle routing quickly, another might draft responses, a third might review policies, and another might recover from errors. The goal is to assign models based on their strengths and the autonomy their role requires. This figure shows how different models can be assigned to distinct roles within an agent system. Each model family handles a specific task, such as routing or policy review, allowing the system to leverage diverse strengths rather than relying on a single model for all jobs. Before optimizing or compressing models, you need to understand what work the model will do inside the agent loop and what constraints it faces. Optimization only makes sense once the model choice is grounded in the system's operational needs, not just leaderboard rankings. Agent workloads differ fundamentally from ordinary chat or completion tasks because they involve ongoing decision-making rather than isolated exchanges. Understanding this difference helps clarify why agents require more complex handling of time and state. In typical chat, each turn can be treated as a separate completion problem. The user asks a question, the model answers, and that's usually enough for that exchange. Agent workloads, however, must carry a task forward through many cycles, remembering what's happened, integrating new information from tools, and deciding the next step based on the whole accumulated situation. The key difference lies in state. Unlike casual context, which is just text and a prompt, agent state is a structured record tracking what the user requested, what constraints exist, what actions were taken, and what results came back. The model must interpret this serialized state carefully to maintain coherence and make the right next decision. A model that sounds fluent in one exchange might still fail as an agent if it can't maintain commitments across multiple turns. Agents must handle noisy or partial tool outputs and keep aligned with the task despite changes. This need for reliability under iteration is more important than just sounding polished. Unlike chat models that only generate language for reading, agents produce outputs that trigger real operations, like searching databases, invoking calculators, or updating state. This means the model must know when to ask for more info, when to pause, and when to avoid guessing beyond current evidence, making it part of a controlled execution process. The best agent models are those that behave predictably across repeated decisions, handle serialized state well, and respect bounded autonomy. The challenge isn't how many tokens the interaction contains, but how many times the system must decide, act, observe, and continue without losing control of the task. This topic compares models to team members, each having distinct roles. Understanding this helps us assign models effectively, just like staffing a team with the right skills for each task. Models are not interchangeable tools. Just as people excel at different tasks on a team, models perform best when assigned distinct roles. Some models draft polished responses, others route requests quickly, and some handle exceptions. Defining clear jobs and how each model escalates issues makes the system more effective. In multi-agent systems, one model might interpret requests, another drafts answers, and a third manages sensitive cases. The routing model needs speed and reliability, not eloquence. The drafting model requires fluency and synthesis skills. The exception handler must judge ambiguous situations carefully. Each role demands a model suited to its unique challenges. Relying on a single powerful model for every function creates problems. It increases costs and slows responses. It also blurs accountability, making it hard to identify where errors occur or optimize individual stages. Assigning specialized roles lets us evaluate each model based on its actual tasks, improving clarity and efficiency. Beyond skill, models differ in how quickly they escalate or how much effort they expend before deciding. Some roles should be conservative and escalate early, while others can take more time to deliberate. Matching these behaviors to roles creates a healthier system with clear boundaries and escalation paths, turning the metaphor into practical architecture. Understanding how a task unfolds over time, the latency limits and deployment restrictions is essential for choosing the right model. These factors influence not just model accuracy, but also practical feasibility and cost. The suitability of a model depends on how the task behaves over time, not only on how hard the input looks. Some tasks need just one strong inference reused multiple times, while others, like agent workloads, require many iterative inferences. Because each step may trigger a new model call, latency and throughput become critical factors, affecting cost and performance in repeated loops. Deployment conditions strongly influence which model to pick. Even a technically excellent model might be unsuitable if the environment demands local hosting, strict privacy, cost limits, geographic controls, or flexible integration. Closed deployment paths reduce operational overhead but limit control, while open paths offer more freedom but require more management. The best choice depends on the agent's goals and the organization's control needs. Different roles in a system come with unique demands. A high-frequency router needs speed and cost efficiency, while a rare escalation model prioritizes capability over speed or cost. Systems managing sensitive data require tighter operational control, whereas others might value rapid updates and scalability. These practical constraints determine which model families fit which roles safely and effectively. A good rule is to match the model to the primary constraint of its role. For frequent, narrow tasks, choose smaller, faster models that reliably meet thresholds. For infrequent but critical roles, pick models that handle ambiguity and recovery well. When privacy or compliance dominates, let deployment options narrow your choices before comparing capability. Model selection becomes a multidimensional decision balancing task shape, budget, and governance. Decoder-only models serve as the fundamental architecture for loops that drive action-oriented agents. Understanding why they fit naturally into this role helps us see how agents make decisions and act sequentially. A decoder-only model generates output by predicting each next token using all tokens generated before it. This step-by-step generation mirrors how an agent moves through a sequence of decisions, deciding, acting, observing, and then deciding again based on the updated context. Because the model generates tokens sequentially, it can produce a plan, request a tool's output, then integrate the returned information before continuing. This flow fits perfectly with bounded autonomy systems, where a controller validates actions and updates state between each step, allowing smooth orchestration without breaking the generation process. These models have become the backbone for interactive systems like chatbots, code generation, and planning tools because they naturally support incremental updates. When a system needs to act, observe, and then refine its next move, the decoder-only architecture allows this interaction to be serialized cleanly and managed turn by turn. The key operational insight is that decoder-only models generate output from left to right and can be paused and resumed after receiving new observations. This makes them ideal for controlled, stepwise decision-making loops rather than one-shot transformations. The following discussion will explore how to optimize these loops and assign specialized roles around this architectural fit. Causal self-attention is the key mechanism that enables models to generate sequences one step at a time. Understanding this helps explain why decoder-only models behave incrementally and produce outputs in a left-to-right fashion. The incremental behavior of decoder-only models comes directly from causal self-attention. This mechanism restricts how tokens attend to each other during generation, enforcing a strict order that prevents future tokens from influencing the current step. This equation shows the core of causal self-attention. The attention weights come from scale dot products of queries and keys, but with an added causal mask. This mask blocks attention to future tokens, ensuring the model only looks backward in the sequence. The causal mask is what makes the model autoregressive. It prevents each token from attending to any token that comes after it, so the model must generate tokens one at a time from left to right. This restriction means the model can't solve the entire sequence at once, but must extend the sequence step by step. For agents, this left-to-right constraint is useful because the agent state can be serialized in the prefix. The model then continues from that state, respecting the order of events. It can incorporate user requests, previous actions, and observations to generate the next step without rewriting the past. The model has no way to fix errors or contradictions in the prefix. If the serialized state is messy or incomplete, the model will base its next decision on that flawed information. This makes careful state serialization and disciplined orchestration essential for reliable sequential decision-making. As the agent runs longer, the history it conditions on grows. This means that every new decision depends on the quality of all prior state handling. The causal mask enables this sequential behavior, but the overall system's performance depends heavily on maintaining clean, coherent state throughout the process. Choosing between open-weight models and closed-service models is a fundamental decision when selecting a model family. This choice shapes how much control you have over the model's life cycle, its visibility, data handling, and your reliance on external providers. An open deployment lets you host and adapt the model yourself, giving you full control and observability. In contrast, a closed deployment reduces your infrastructure needs and can speed up access to powerful capabilities, but it limits how much you can customize or monitor the model's behavior. When dealing with sensitive data or regulated workflows, controlling where and how inference happens is critical. Sometimes, this control is more important than having the very latest model features. On the other hand, if speed and simplicity matter most, managed services provide strong models without the overhead of maintaining your own infrastructure. You can think of open and closed models like staffing choices. Some tasks benefit from a scalable, easy-to-use service, while others need a model deployed under strict control. This perspective turns openness into a systems trade-off about control, customization, and dependency rather than a simple preference. Neither open nor closed deployment is inherently better. The right choice depends on factors like latency requirements, privacy needs, cost constraints, and how much integration freedom your workflow demands. Because of this, deployment path is part of the model family decision from the start, shaping how the model fits into your agent architecture. This part explains how the underlying architecture of a model affects its ability to use tools, handle branching decisions, and fit within control flow structures. Understanding this helps us see why some models work better as agents in complex workflows. Models rarely follow a straight path in agent loops. They often need to pause, ask for clarification, pick tools, or recover from errors. A good model fits naturally into these branching patterns without confusing the controller. Some models are easy to guide into clear actions, while others wander or mix explanation with action. This fit is crucial because the control layer depends on the model style, matching the decisions it must make. Using tools quickly exposes whether a model fits the workflow. The model must know when to call a tool and how to use its output. If it's too loose, it might jump ahead, assuming results are final. If it's too hesitant, it delays needed actions. The best models balance quick decisions with careful observation, maintaining discipline. This balance comes from the model's architecture and behavior, not just its vocabulary. Branching also relies on recovery, pausing, retrying, checkpointing, and resuming. Models must continue based on what already happened, not treat each turn as new. Models that reimagine the whole task each time are hard to control. Models that respect the serialized decision history let controllers trust the next step fits the current branch. This is vital when workflows involve approvals, partial failures, or delays. The key test for architecture is whether the model supports cycles of deciding, acting, observing, and recovering. It must stay disciplined when options narrow and produce structured outputs so the controller can branch safely. These conditions decide if a model family can serve as an agent backbone. The essential question is whether the model can participate in the loop without breaking its structure. Role specialization allows different models within a multi-agent system to focus on tasks that suit their strengths. This approach improves efficiency and overall system performance by assigning clear responsibilities. When model choice is treated like staffing, each model doesn't need to do everything. Smaller or faster models can efficiently handle routing and basic classification, which require consistency and speed. Larger models are reserved for complex cases where careful reasoning or handling ambiguity is critical to avoid errors downstream. Each role in a multi-agent system has unique demands. Routers must be fast and reliable since they guide the workflow. Drafting roles require richer language generation and synthesis. Review or escalation roles need to be cautious and good at spotting when human intervention is necessary. Assigning models to roles they excel at leads to better performance than using one model for all tasks. When all tasks use the same model, it becomes hard to understand why the system behaves a certain way. Specializing roles makes it easier to pinpoint problems. If routing fails, you know the routing role needs attention. If drafting is weak, the drafting role is responsible. This separation also allows better cost management by matching model size to responsibility. The best practice is to assign the least expensive model that can reliably handle a role, then use more capable models only where their extra reasoning changes outcomes. This staffing approach ensures efficiency and preserves escalation paths for difficult cases, improving both cost and quality in multi-agent systems. Choosing the right model family for an agent involves balancing multiple factors. This part covers a practical checklist to guide that choice and previews the trade-offs we'll explore in this chapter. Begin by understanding the tasks the system must repeatedly handle, the actions those tasks trigger, the state that needs to persist, and the control boundaries that must be enforced. Then select a model family that fits smoothly into this control flow. Frequent, narrow roles benefit from speed and predictability, while rare but important roles need models that allow more judgment and recovery. Deployment constraints like privacy or governance should also influence the choice. Decide if the model will perform a single role or multiple roles. For example, a routing model requires different criteria than a deliberation model. Similarly, drafting models and policy gates serve distinct purposes. In systems with multiple models or agents, clearly assigning roles and managing handoffs helps combine specialists and generalists effectively without losing control. This chapter will explore how different model families work internally, how state and history affect long-term use, and how efficiency impacts deployment costs. It will also address scaling specialized roles. Remember, benchmark performance is important, but only one part of a broader design problem involving task demands, serving and governance constraints, and clear role assignments. This part explains how decoder-only models generate text, how they share attention computations efficiently, and the economic trade-offs involved in managing key value caches during generation. Decoder-only models have become the standard choice for building agent backbones because their design fits naturally with how agents operate over time. Understanding this alignment reveals why they outperform other architectures in agent tasks. Agents don't just take a single input and produce a one-off answer. Instead, they work in a cycle. They read the current state, generate a bit of text, pause to interact with tools or humans, and then continue from where they left off. This ongoing interaction matches perfectly with decoder-only models, which are designed to extend text one token at a time rather than transform an entire input in one step. This figure illustrates how decoder-only agents operate as continuation engines. Each generation step adds to the existing prefix, then pauses for tool calls or human review, before resuming generation based on the updated conversation. This cycle supports incremental reasoning and action seamlessly. Choosing the right model for an agent is about more than just how good its outputs look. The architecture must support the control flow the agent requires, like drafting summaries, calling tools, absorbing results, revising plans, and producing responses, all as extensions of an ongoing sequence. Decoder-only models naturally fit this pattern because they allow the same forward pass to serve multiple roles in reasoning, acting, and continuing execution. Agents often need to call the model multiple times within a single task for deciding on tool calls, interpreting results, generating structured responses, or asking for approval. This repeated use demands a model architecture that can handle many small continuation steps efficiently. Decoder-only models excel here, while architectures optimized for single long passes may struggle with latency or cost when called repeatedly. When multiple agents specialize into roles like a fast router, a deliberative planner, or a control function, they implicitly select different model sizes and capabilities to fit each role's demands. The router needs speed and low cost. The planner requires deeper reasoning, and the control role values predictable outputs. Decoder-only models provide a common backbone that supports incremental continuation across all these roles, even though one large model rarely fits every need economically. Autoregressive generation means the model predicts one token at a time, always conditioning on the tokens it has already produced. This process underpins how decoder-only models generate text step by step. The model reads the existing text, then calculates a probability distribution over all possible next tokens. It doesn't produce the whole answer at once, but picks one token, adds it to the input, and repeats this cycle. This chain of local predictions creates the full output sequence. Because the model commits only to the next token at each step, it can pause and insert clarifications or tool calls easily. When new information arrives, generation picks up from the updated prefix. This makes the model behave like a stateful engine, not a one-shot translator, which is crucial for interactive agents. The model can mix natural language, plans, tool commands, and responses seamlessly because they're all just tokens in the same sequence. Planning isn't a separate module, but emerges naturally as the model conditions on prior steps and outputs, simplifying the interface between reasoning and execution. At each step, the model outputs a vector of scores for all tokens, called logits. How these scores translate into the chosen token depends on the policy used. The key is that every decision commits to just one token, building the sequence incrementally. This makes the architecture practical for conversation, but also means each token depends on all previous tokens unless optimized. Causal self-attention enforces a strict left-to-right flow in decoder-only models, ensuring tokens are generated in sequence without future information leaking backward. The position a token occupies determines what it can see. Earlier tokens can affect later ones, but later tokens cannot influence earlier ones during generation. This preserves the autoregressive property, making sure no token is generated using information that doesn't exist yet. This constraint is made concrete by modifying the self-attention calculation with a mask that blocks attention to future tokens, ensuring the model respects the generation order. Here, Q, K, and V are the query, key, and value matrices. The causal mask, M_causal, adds negative infinity to positions representing future tokens, effectively zeroing out their attention weights. When generating the token at position T, the model can attend only to tokens from 1 up to T, but not beyond. This means the output at each position is a weighted combination of previous values, ensuring the model builds its prediction from past context alone. This figure illustrates how each token's attention is restricted to earlier tokens. The shaded areas represent allowed attention, while the masked-out future tokens are blocked, preserving the left-to-right generation order. For an agent generating text, This mask guarantees that early tokens can't rely on decisions made later in the sequence. While the agent might revise outputs after external information arrives, each generation pass respects the left-to-right constraint, maintaining coherence in streaming responses. Think of the model's attention as a ledger that only looks backward. It can accumulate evidence from earlier tokens, but can't change what's already recorded. This is why agents often store state externally, because the model itself can't remember or revise future context without explicit input. Naive recomputation means recalculating everything from the start for each new token. This wastes both time and bandwidth, making the model inefficient and slow, especially in interactive settings. If the model reprocesses the entire prefix every time it generates a new token, it ends up repeating the same work over and over. This not only consumes extra compute, but also overloads memory bandwidth by moving the same data repeatedly through the network. In a conversation where the model pauses to get tool results, it must replay all prior messages and tool outputs from scratch to generate the next token if no caching is used. This is like rereading the whole transcript just to add a single sentence, which slows down responses and raises costs. As conversations grow longer, the cost of recomputing all previous tokens for each new token becomes more severe. This causes latency to rise with conversation length, making the system feel sluggish and less responsive over time. Recomputing history means passing large activation matrices through the attention layers repeatedly. This saturates memory bandwidth, even if compute is sufficient. KV caching helps by avoiding this repeated data movement, improving generation speed and efficiency. KV cache mechanics explain how transformer models reuse previously computed data to speed up generating text one token at a time. Understanding this process reveals why incremental decoding is efficient and practical for interactive tasks. KV caching saves the key and value tensors computed for each token during the initial decoding pass. When a model generates the next token, it avoids recalculating these states for the entire prefix. Instead, it only computes new projections for the new token and appends them to the cache, attending over the accumulated data. This avoids redundant work and speeds up generation. Think of the cache as a ledger that keeps track of all intermediate results instead of replaying everything from scratch. It's not long-term memory or a saved checkpoint, but a temporary store of tensors that lets the model build on previous work. This is crucial for agent tasks where the conversation grows over multiple turns, allowing the model to efficiently keep context without repeating computations. Each transformer layer adds its own keys and values to the cache. So the store data grows not only as more tokens are processed, but also with the number of layers. This layered structure means that even generating one token at a time can consume significant memory over a long session. Managing this memory is a critical concern in serving models efficiently. Instead of recomputing the entire prefix for every new token, incremental decoding pays a one-time cost to build the cache, and then a smaller cost for each token generated afterward. This makes interactive reasoning feasible, especially when a model pauses for external actions and later resumes from the cache state, maintaining efficiency across multiple turns. KV caching fundamentally alters how agents handle conversations that span multiple turns or involve external tools. It lets the system maintain context efficiently across interruptions and tool calls, which is crucial for complex interactions. When an agent like Atlas drafts part of a response, pauses to call a tool, then resumes, KV caching allows it to continue from the existing context. Without caching, the model would need to recompute all prior representations, but caching attaches the new segment to the saved state, making the process much more efficient. Agent systems often pause when they have already gathered significant context, such as waiting for human approval or a slow external API. Keeping the prefix state alive through caching avoids repeating expensive computations and enables smooth, interruptible agent loops that can pick up exactly where they left off. Even if each agent output is short, the cache grows with every turn, accumulating more tokens and state across layers. This means long-running sessions can become limited by memory before compute, affecting deployment decisions like batch size and concurrency. While caching avoids recomputing previous tokens, it still requires storing and processing the entire accumulated context. This means very long conversations or verbose tool outputs can slow down the system. Caching shifts the challenge from replaying everything to carrying everything, which improves efficiency but does not remove all scaling issues. Group query attention introduces a way to reduce memory costs in multi-head attention by sharing key and value projections among query heads. This approach balances efficiency with maintaining rich query expressiveness. In standard multi-head attention, each head has its own query, key, and value projections, which can be costly. Group query attention lets many query heads share a small number of key and value heads. This keeps the model's ability to ask diverse questions while cutting down the amount of stored key value data, which directly lowers cache size and memory bandwidth needs. The cache holds keys and values because those represent the persistent memory of past tokens, while queries are generated on the fly for each step. By allowing multiple query heads to share the same key-value pairs, the model avoids duplicating this stored state. This reduces the memory footprint and the bandwidth needed to access the cache during decoding, which is often the main bottleneck in runtime performance. Agent systems frequently revisit past information, such as user requests, tool outputs, and conversation history. This repeated access can cause heavy memory traffic if the key-value cache is large. Group query attention reduces this traffic by shrinking the cache size, making it easier to deploy agents at scale with less memory pressure during decoding steps. While GQA makes the model's memory usage more efficient, it doesn't improve the model's understanding or the quality of its responses. It's a tool for serving more requests or reducing latency, not for fixing issues like noisy context or poor prompt design. Think of it as a way to lighten the computational load, not a way to choose better evidence or improve reasoning. This part explains how a small piece of configuration data reveals how a model organizes its attention heads and what that means for its runtime behavior. Even a tiny excerpt from a model's configuration can tell us a lot about how grouped query attention, or GQA, actually works in practice. This snippet shows two key numbers. The model has 28 query attention heads, but only 4 key value heads. This means multiple query heads share each key value representation. Because there are many more query heads than key value heads, the model groups queries around fewer key value streams. This reduces the memory needed to store key value pairs during decoding. This ratio means the model keeps a wide query space, but limits the number of key value streams it must store. That lowers memory use and bandwidth when processing longer contexts, making the model more efficient. Counting heads is more than a technical detail. It shows where runtime costs arise and explains how the same model can perform well both in quick drafts and in longer planning tasks without excessive memory use. This part explores how caching affects the speed, capacity, and memory demands of serving models. Understanding these factors helps balance performance with resource limits. Latency is the delay a single user experiences when waiting for a response, while throughput is about how many requests the system can handle at once. Caching key value pairs reduces repeated computation, improving both metrics, but the effects vary depending on usage patterns and system setup. Each token stored in the cache uses memory across multiple layers, so as conversations get longer, the total memory needed increases. This limits how many sessions can run simultaneously, especially for agents that keep extensive state and intermediate results compared to simple text generation. Reading cache data at each step can become a bottleneck before computation does. This means that even with powerful hardware, performance gains may stall if the system can't move cache state efficiently. Architectural choices that reduce persistent state movement can therefore have a big impact on real-world speed. Faster decoding makes agents feel more responsive, but each active conversation consumes memory and bandwidth. The choice of model and serving design must consider how long agents stay active, since the cache becomes a significant part of operational cost, not just an internal detail. Cache efficiency helps reduce the cost of handling context, but it doesn't guarantee that the context is actually useful. This is a key limitation when dealing with large amounts of information. Even if a system can efficiently store and access a large context, that doesn't mean the context helps the model make better decisions. When the context grows too large, relevant information can get lost among irrelevant or outdated details. A cheaper cache just makes it easier to revisit all that information, but it doesn't help the model figure out which pieces actually matter. Managing which information stays in the working context is a different challenge than optimizing how fast the model generates responses. A system can have a very efficient cache, but still perform poorly if it includes outdated instructions or noisy data. Improving cache speed alone won't fix problems caused by cluttered or irrelevant context. Having a longer context window might seem beneficial, but it only helps if the system can pick out the right evidence to use. Otherwise, adding more information just makes the useful details harder to find. For example, dumping every previous search or note into the context can overwhelm the model and reduce its ability to make the correct decisions. It's important not to confuse the model having access to more information with the model actually using that information well. Techniques like KV caching reduce computation time, but don't solve problems like distractions or stale data. If the working context is poorly organized, the system might seem efficient but still make worse decisions, which can be confusing. This part examines how the efficiency of encoder-decoder models compares to decoder-only models, highlighting their different execution styles and use cases. Decoder-only models are popular for chat and agent tasks because they generate output incrementally, continuing from previous tokens seamlessly. Encoder-decoder models, however, separate the process into encoding the input first, then decoding the output, which can be better when input and output serve different roles, or when the task is about transforming sequences rather than continuing them. Some modern encoder-decoder architectures improve efficiency and handle longer contexts well through special optimizations. Yet, for agent workloads that rely on repeated incremental generation, decoder-only models remain more practical. Their runtime behavior, especially cache usage, directly impacts latency and cost in these systems. This comparison shows that no single model type owns efficiency. Different architectures distribute computation differently. In real applications, the key question is whether the model's generation loop, caching, and responsiveness fit the specific workload. For stateful, interactive agents, decoder-only models often align best, making their causal attention and key value caching critical. This part focuses on practical guidelines for designing agent systems that work efficiently in real-world production environments. Understanding these heuristics helps balance performance and resource use. Choosing the right model goes hand in hand with how you serve it. A model that looks good, theoretically, might be too costly to run for long sessions, while an efficient model can still fail if the context it receives is not well managed. Think of the system as layers. The decoder generates output incrementally. Key-value caching makes this generation affordable. Grouped query attention reduces caching load, and context design ensures the model focuses on relevant information. Caching shines when a model often returns to a previously generated prefix, like during multi-turn conversations or when the agent pauses for tool calls or human input. The more frequent these interruptions, the more you benefit from keeping the working data in cache. For short or one-shot interactions, caching still helps but is less critical. As conversations get longer, the key challenge is maintaining responsiveness without running out of memory or bandwidth. If the model runs slowly because it recomputes history too often, focus on improving incremental decoding, reusing key-value caches, and using attention methods like group query attention. But if the model is fast yet produces confused outputs, the problem lies in what state is fed into the prompt and how outdated information is handled. Mixing these issues leads to wrong fixes. Speeding up cache won't solve prompt overload, and better prompts don't replace the need for efficient caching. For building agents, the practical takeaway is to pick model families that handle your expected repeated control flow well. Your serving infrastructure should be sized to handle the cache footprint this flow creates. Meanwhile, your context strategy should prune irrelevant information so it doesn't consume valuable working memory. Decoder-only generation, causal masking, key-value caching, and group query attention are the core techniques that make repeated interactions feasible and cost-effective. Understanding the difference between long context and effective context is crucial for designing agents that perform well. This part explains why simply increasing the context window size can actually create challenges instead of improvements. Having a bigger context window means the model can process more tokens at once, but that doesn't ensure it will use that information effectively. Larger prompts can overwhelm the model with irrelevant details, making it harder to pick out what actually matters. This creates a more difficult inference problem where the model must carefully assign attention and suppress noise to act correctly. This figure contrasts raw token capacity with effective context. Notice how a larger prompt can bury important evidence in noise, making it harder for the model to focus. In contrast, a carefully curated prompt highlights the relevant information, leading to better decisions. In practical agent scenarios, like a travel assistant, including every past detail can confuse the model. Old or conflicting facts may compete for attention, causing uncertainty about what should guide the next action. Without careful pruning, the model struggles to resolve these conflicts consistently. Tasks like summarization tolerate broad context, but agents making operational decisions need focused, relevant information. A shorter prompt with the right state and constraints often outperforms a longer, cluttered one. The model's capacity only helps if the context remains meaningful and actionable. Effective context management means knowing which tokens inform decisions, which support traceability, and which should be removed. Without this discipline, context just accumulates and degrades performance. Agents should keep active context small and precise, store execution artifacts externally, and retrieve evidence only when needed. This approach is essential to solving the haystack problem. Longer prompts might seem like they should improve an agent's performance by providing more information. However, adding too much context can actually cause problems that reduce accuracy and reliability. When a prompt includes many unrelated or loosely related details, the model's attention can get scattered. Instead of focusing on the key rule or fact it needs, the model might give weight to less relevant parts, leading to confident but incorrect decisions. Even if the important information is present, it can be hard for the model to pick it out when it's buried in a noisy or repetitive context. This is common in agents that use multiple tools, where fresh but less relevant details might overshadow the critical facts. Long prompts often accumulate conflicting statements, like different priorities or corrections. Without a clear rule about which version is authoritative, the model can flip between interpretations or make inconsistent choices, reflecting a deeper problem in managing state. A large prompt can give the illusion that all information is up to date. But models don't reason like humans. They rely on distributed representations that don't automatically mark freshness. This can cause outdated facts to influence decisions long after they should be ignored. To manage prompt length effectively, consider whether each piece of information is useful for the next step, must remain visible, or can be retrieved again if needed. This approach turns more context from an automatic benefit into a deliberate engineering trade-off. Understanding the different layers of context in agent systems helps us design more efficient and reliable AI. This part clarifies key terms to separate what the system actively uses from what it stores or retrieves. Active working context contains everything the model requires right now to decide its next step. It includes instructions, the current task setup, a brief state summary, recent interactions, and any evidence directly relevant to this moment. This context should be concise and focused on what matters immediately. Archival state differs from active context because it holds execution details like past tool calls or decisions. This data is stored outside the prompt so the system can resume or audit runs later. It's about operational continuity, not influencing future behavior directly. Retrieved evidence comes from external databases or knowledge bases when needed. It's temporary and relevant only for the immediate decision. For example, policy texts or FAIR rules might be fetched for a single query and then discarded once the topic changes. Long-term memory stores information that lasts beyond a single session, like user preferences or historical patterns. It supports personalization, but should not clutter active prompts. Instead, it's managed separately and only injected when relevant to keep the working context lean. Confusing these layers leads to poor design. Treating archival state like memory wastes effort on transient details. Treating memory like active context clutters prompts with irrelevant facts. Treating retrieved evidence as intrinsic state risks losing traceability. Clear boundaries ensure each layer works as intended. Think of these layers as physical spaces. The desk is your active context, cluttered if overloaded. The filing cabinet holds archival state for recovery. The library is where you retrieve temporary evidence. The notebook stores long-term memory. Good design places information in the right space and moves it only when needed. This figure illustrates the four distinct layers of agent context. The live prompt is the active workspace. Archival state is stored safely for recovery. Retrieval brings in external evidence as needed, and durable memory holds lasting information. Managing these separately keeps the system efficient and clear. The haystack problem happens inside attention mechanisms when the model struggles to pick out relevant information from a growing set of tokens. Understanding this helps explain why long contexts can be challenging for models. Attention works by focusing on the most important parts of the input, but it has limited capacity. When the sequence gets longer, the model has to spread its focus across more tokens. Even if the important tokens are still there, they compete with many irrelevant or weakly relevant ones. This competition lowers contrast, making it harder for the model to clearly distinguish what matters. So, the issue is less about losing information and more about the model's difficulty in discriminating the right evidence. Many developers think that when models fail on long contexts, it's simply because the model runs out of memory. But the model isn't just storing tokens like a hard drive. Adding more tokens changes the way information interacts inside the model. More context can create accidental correlations and redundant phrasing, which can trick the model into focusing on plausible but incorrect clues. So, making the context bigger doesn't automatically make the important information easier to find. This problem shows up clearly in how agents behave. For example, the model might pick a tool that seems to fit a nearby pattern rather than the one that actually fits the current need. It might recall recent fragments instead of the most reliable information. Or it might combine too many pieces of evidence into a vague answer that is technically correct but practically wrong. These failures don't mean the model can't handle the task. They mean the model can't clearly separate the right information from the rest. The haystack problem becomes more obvious in agents that manage complex workflows. Unlike simple chat completions that just respond to the latest sentence, these agents keep track of user intent, prior decisions, tool outputs, and constraints. These elements differ in how current or authoritative they are. The model must understand not only the content, but also the structure of this conversation state. Without clear distinctions encoded in the prompt, the model struggles to treat some tokens as more important than others. The key practical point is that long context is useful only when the system keeps what matters clearly visible. If relevant information fades into the background, the model might still be aware of it, but unable to use it effectively. This is the haystack problem in action. The information exists, but the model can't reliably pick it out when it needs to make a decision. Context management is more than just editing prompts. It acts as a runtime policy layer that governs how information is handled during execution. This means deciding dynamically what information to keep, summarize, retrieve, or discard to guide the system's behavior effectively. The quality of the context is just as important as how much context you have. The system must carefully choose what to keep exactly, what to summarize, and what to remove. These decisions influence how the agent acts next, how it resumes after interruptions, and how it stays true to reliable information. So, context management is integral to how the system executes tasks. A good policy starts by pinpointing what information is essential right now. For example, Alice might need the current user goal, the trip draft, the latest budget, and binding policies. Other details should be evaluated for necessity. Audit information goes to archives. Reusable but not immediate data can be retrieved later, and temporary results might be better summarized to save space. Summaries compress information, trading off detail for brevity. This is fine when summaries serve as working sketches, but risky if they replace the original facts. For instance, a summary saying the user prefers budget options can guide search, but it shouldn't overwrite the original requirement if the user later changes their mind. Summaries are convenience layers. not authoritative sources. Instead of storing everything in the prompt, retrieval fetches relevant evidence on demand. This requires a retrieval layer that ranks and filters candidates well before adding them back into context. The goal is not to avoid context, but to use it efficiently, focusing only on what matters now. This approach also keeps the conversation history clean and purposeful. The key question is how to make information available again in the most cost-effective way. Sometimes keeping the exact text is best if the detail is small and authoritative. Other times, storing a compact state, an identifier for retrieval, or long-term memory is better. Context management is the policy that chooses the right approach for each piece of information. KV cache reuse is a key technique for efficient autoregressive generation, but it also introduces hidden costs that affect system performance and correctness over long-running interactions. During autoregressive generation, the model avoids recalculating every intermediate step by storing key and value tensors from previous tokens. This cache lets the system extend sequences incrementally instead of starting over, which greatly improves throughput and reduces latency, especially for agents that mix reasoning, tool use, and response generation. The downside is that the cache grows as the sequence gets longer, consuming more GPU memory. In small tests, this may seem trivial, but in production, long conversations with many turns and tool calls can tie up memory. This reduces the system's ability to handle multiple requests simultaneously, making it less efficient and more costly. So managing the cache is not just about speed, but also about planning capacity. Correctness also depends on the cache being valid only for the exact token sequence and their positions. If the prompt changes structurally, like adding an approval step or rewriting instructions, then reusing the old cache blindly can cause errors. This is especially important in dynamic agent systems where prompts are assembled on the fly. Cache reuse must happen only when the context matches perfectly. Consider a travel planning agent revisiting a trip itinerary multiple times. Each update, like adding search results or inserting approval notes, may change what the model should trust as current. If the cache is reused without care, it might speed up the wrong computations. But invalidating too often wastes effort and slows things down. The goal is to reuse as much cache as possible while precisely invalidating only what's outdated or unsafe. Cache behavior should be treated like any critical resource. If memory usage climbs steadily, it signals too much context baggage. Throughput drops when prompt patterns vary, indicate unnecessary recomputation. Response time swings between cache hits and misses suggest inconsistent prompting. KV cache reuse only improves performance when the surrounding context policy is carefully managed to keep it reliable and efficient. This part covers 4 key techniques that optimize how models handle input sequences and workload. Understanding these helps keep systems efficient and responsive under different conditions. Prefix caching saves effort by remembering the processing done on shared starting text across multiple requests. This works well when parts like system instructions or task framing stay consistent. However, if the prefix changes often or includes random variations, the cache becomes less useful. Processing very long inputs all at once can cause delays and memory issues. Chunk prefill breaks the input into manageable pieces, allowing the system to schedule work more flexibly and keep things running smoothly. This is especially useful when handling large documents or long histories, though it requires care to avoid confusing the model at chunk boundaries. Instead of waiting for fixed batches to fill before processing, continuous batching allows incoming requests to join batches already running. This keeps hardware busy and adapts to varying request sizes and timing. But it complicates fairness and latency guarantees, so the batching strategy must balance efficiency with user experience needs. When context length approaches limits, sliding windows discard or compress older parts of the conversation to maintain a manageable input size. This keeps recent, relevant information accessible while preventing memory overload. Choosing what history to keep is critical because losing important early context can cause errors or brittle behavior. Prefix caching cuts down repeated work. Chunked prefill smooths large inputs. Continuous batching boosts hardware use. And sliding windows keep context size in check. Together, they enable agents to manage complex prompts and multi-turn tasks efficiently. But relying on them without good prompt design risks preserving too much unnecessary text, which can degrade performance. This part explains why a system must selectively invalidate cached data when the structure of the input context changes, rather than reusing cache blindly. Understanding this helps maintain correctness when prompts evolve dynamically. Prompts and dynamic agents don't just grow longer, they change shape. New information can be added, instructions rewritten, or parts removed. When prompts stay fixed, caching is straightforward. But when they mutate, the existing cache may no longer fit the new prompt structure, so reuse requires careful checks. When an agent rearranges parts of the prompt during processing, like moving a recent draft before older notes, it changes the order and relationships between tokens. This can make cache segments invalid because their positions no longer match. If the system reuses stale cache, the model might get confused by inconsistent internal states. Adding or removing tokens obviously requires invalidation, but changing the order is just as critical. The sequence order shapes how the model interprets input. Moving a keynote closer to the current action helps the model focus but breaks alignment with old cache data. Effective caching must understand these structural changes, not just whether content was appended. It might seem efficient to keep as much cache data as possible to save recomputation time. But reusing stale cache can cause wrong outputs, especially when agents interact with external tools. Correctness is more important than speed. Cache reuse should happen only when the prompt structure matches perfectly, avoiding subtle errors that slow down or break the system. Cache metrics reveal how well an agent manages its conversational context. Understanding these metrics helps diagnose inefficiencies in prompt design and memory use. A high cache hit ratio means the system is effectively reusing stable parts of the prompt, like repeated instructions or prefixes. If the hit ratio is low or unpredictable, it often indicates the prompt changes too much or carries too many variations, which prevents efficient reuse. Ideally, a well-designed agent maintains a consistent conversation pattern, which the cache behavior should mirror. When memory usage grows steadily over a session, it suggests the agent holds onto too much active context or fails to remove old information effectively. This is especially critical when the agent combines document retrieval with reasoning, since retrieved content and tool outputs can be large. If new tokens accumulate without improving future decisions, the system wastes memory on irrelevant history rather than useful context. When the cache works well and context stays compact, the system responds quickly and predictably. But if prompts become bloated and cache reuse drops, response times become inconsistent. This unpredictability harms user trust and complicates orchestration, since the agent sometimes responds fast and sometimes stalls due to wide prompts. Stable context management avoids these latency spikes. Instead of blaming infrastructure for poor cache hit ratios or high memory use, treat these metrics as feedback on how the prompt is structured and managed. Frequent prompt changes lower cache effectiveness, and retaining too much history wastes memory. Viewing cache metrics this way turns them into tools for improving context design rather than just monitoring system health. Understanding where encoder-only models fit in an agent architecture helps clarify their unique role and strengths compared to other model types. Encoder-only models are designed to analyze and understand input data deeply. They perform best on tasks like classification, re-ranking, and creating embeddings, which involve interpreting content rather than generating new text step by step. In practical agent systems, these models serve as readers and indexers. They help rank documents, identify relevant passages, or classify inputs before passing a refined set of information to a generative model for further processing. Because encoder-only models can efficiently handle large amounts of text to find relevant content, they reduce the workload and expense of generative models. This separation is especially useful when an agent frequently consults large document collections. This division clarifies the workflow. Encoder-only models select and understand relevant input, while generative models focus on producing coherent and useful output. Keeping these roles distinct improves reliability and makes managing long context easier. Masked language modeling trains encoder-only models to predict missing tokens using both left and right context. This bidirectional approach enables deeper understanding of text passages, which is crucial for tasks like document matching and policy interpretation. Instead of predicting the next word step by step, these models mask some tokens and learn to fill them in using context from both sides. This encourages the model to view the input bidirectionally, which is exactly what you want when the goal is to understand or analyze text rather than generate it. Because these models don't generate tokens one after another, they don't need to keep track of a growing output sequence. This makes them well suited for tasks where the input is fixed and the output is a concise label, score, or vector, such as classifying intent or measuring relevance in a retrieval system. Because the model isn't distracted by generating text, it can devote its full capacity to understanding the entire input sequence. This helps in retrieval scenarios where fine semantic differences matter, like distinguishing which policy passage applies exactly, even if several are similar. Recent encoder-only models build on this bidirectional foundation by handling longer inputs more efficiently. They use innovations like rotary positional embeddings and optimized attention mechanisms, which allow them to process long documents and many candidates quickly, meeting the demands of real-world retrieval and classification systems. Encoder-only models have evolved significantly and remain crucial in modern workflows. This part explains how these models adapt to practical demands and why they form a key part of efficient agent architectures. Encoder-only models are no longer static legacy tools. They have improved their ability to process longer inputs and use memory more efficiently. These enhancements make them well-suited for retrieval tasks where speed and scale matter, especially when scoring long documents quickly. In practical systems, encoder-only models act as filters. For example, they can rank incoming support tickets against policy documents to find the best matches before any text generation happens. This pruning reduces the workload for generative models by narrowing down the relevant context. It's important to distinguish between trimming context for a single run and designing memory that lasts across sessions. Retrieval systems let us keep important information accessible without cluttering the prompt. This way, the prompt stays lean, but the system can still trace back to all relevant documents when needed. A practical rule is to keep only the most critical information in the live prompt. Use retrieval to bring in supporting evidence when necessary. Store archival data separately and reserve long-term memory for facts that influence future interactions. Encoder-only models help by reducing the volume of data before it reaches the generator, keeping the system efficient and scalable. This part explores how rotary positional embeddings, or ROPE, help extend the context length models can handle. Then, we'll examine how computation budgets influence model design and how mixture of experts, or MO, can optimize resource use. ROPE changes how models understand position by embedding it directly into the geometry of attention. This approach lets the model handle order as part of the core computation, not as an add-on feature. Rotary positional embeddings work by rotating the query and key vectors based on each token's position. This means the model doesn't just get a label for position. It experiences position as a change in vector orientation. This helps the model distinguish sequences and understand the order of events precisely. Imagine each token as a point on a coordinate grid that twists gently as you move along the sequence. Instead of adding a separate position marker, ROPE changes the token vectors themselves. When tokens are compared, the angle between their vectors reveals how far apart they are, capturing relative position naturally. Unlike learned position embeddings that assign fixed roles to specific positions, ROPE expresses order as a rotation in vector space. This gives the model a structural advantage to generalize beyond the sequence length seen in training, which is crucial for handling long, complex sequences in real-world tasks. A simple way to think about ROPE is as a rotation applied to the query and key vectors based on their position. This rotation happens before the attention dot product, embedding positional information directly into the vectors the model compares. This figure illustrates how ROPE rotates query and key vectors for each token. The attention mechanism then uses the angular difference between these rotated vectors to infer relative positions, removing the need for separate position labels. Here, Q prime and K prime are the rotated query and key vectors at position T. The rotation matrix depends on the token's position, embedding positional information directly into these vectors before attention is computed. The key advantage of rope is that it preserves the relative offset between tokens through their rotated vectors. This is vital for tasks where the difference in order matters more than absolute position, like tracking which event happened first in a sequence of instructions or updates. Rotation in positional encoding helps the model understand how tokens relate to each other in terms of their positions, not just their content. This makes it easier for the model to handle long sequences where the order and distance between tokens matter. Attention measures how compatible or related two tokens are. When query and key vectors are rotated based on their positions, their dot product reflects not only semantic similarity, but also how their positions align. This helps the model notice if tokens are close together, far apart, or ordered earlier or later in the sequence. Such sensitivity is crucial for tasks that depend on the relationship between facts rather than isolated facts alone. In reasoning tasks, the sequence often represents a compressed history of instructions, observations, and tool outputs. Rope helps the model reconstruct the causal order by indicating whether information is fresh or outdated. This positional signal reduces dependence on exact token locations and provides a smoother understanding of relationships across the sequence, matching the structure of agentic context better. Rope extends the geometry of positional encoding rather than enlarging memory capacity. While it allows attention over longer sequences, it doesn't guarantee better understanding of all past tokens. As sequences grow, maintaining clear relationships between distant tokens becomes harder, and attention must compete among more candidates, some of which may be irrelevant. Even when a model isn't explicitly reconstructing sequences, rope provides useful ordering information. For example, it can help distinguish preliminary notes from final conclusions in a long chain of research. This positional awareness is probabilistic and scalable, improving performance on longer sequences without turning the transformer into an exact timeline recorder. Rope offers a more robust way for models to handle positions and sequences, especially when dealing with longer inputs than seen during training. Understanding why it generalizes better helps us grasp how models maintain performance across varying sequence lengths. Rope works by embedding positions in a way that captures relative offsets through rotations, rather than tying each position to a fixed index. Learned absolute embeddings often cause models to memorize specific positions, which limits their ability to handle longer sequences. Rope's approach creates a positional space that is smoother and easier for the model to generalize across different sequence lengths. When a model learns relationships as phase differences, it can apply the same structural cues even as sequences grow longer. This is why rope is especially useful in tasks like long conversations or multi-step reasoning, where understanding the order and timing of tokens is crucial. The model can recognize sequences like this instruction follows that output, rather than just relying on approximate absolute positions. Even though rope improves generalization, the model still trains on a limited range of sequence lengths. When inputs become much longer, the model's predictions can become less stable or biased toward recent tokens. This means that while the model can handle longer sequences, the reliability of information near the far end of the input window is lower, like looking at a foggy horizon. Rope creates better conditions for reasoning over long contexts, but doesn't guarantee perfect understanding. In agent workflows where state accumulates over many turns, the model's ability to keep track of original constraints depends on how well the sequence supports attention to relevant tokens. Even with a strong positional scheme, managing the prompt effectively is essential to avoid mixing outdated and current information. Scaling context at load time means adjusting how the model handles sequence length when it starts up. This approach lets us extend the model's effective input window without retraining, which is crucial for practical deployment. Rope, or rotary positional encoding, becomes a runtime setting rather than just a design choice. By scaling the frequency schedule used for rotations, the model can interpret longer sequences. This happens in the model loader or serving stack, which modifies the positional transformations but leaves the core model weights unchanged. Essentially, the model's internal language stays the same, but its coordinate system stretches to accommodate more input. The deployment idea can be summarized by setting a scaling factor during model initialization. This lets the model handle longer inputs than it was initially trained for. The scaling happens before any text is processed, making it a foundational configuration rather than something done dynamically in prompts. This code shows how to load a model with rope scaling applied. The key line is the rope underscore scaling parameter, which sets a linear scaling factor of 4. After loading, the model can generate text from a longer input than usual. This approach integrates scaling into model initialization, making it part of the serving pipeline. The important point is that scaling is not magic in the prompt, but a deliberate choice when the model loads. This affects how the application budgets prompt length, manages retrieval, and trusts the model's reasoning. The system must be aware if the model is configured for extended context to handle these implications properly. A model trained on short sequences can still process longer ones with rope scaling, but this is extrapolation. The behavior at these lengths is less certain, so deployment teams should treat scaling as an experiment. Longer windows can help with detailed histories, but also increase latency, memory use, and the chance of distraction from irrelevant content. Careful policies are needed to decide when to use extended context. Extending the window only helps if the application feeds it relevant information. Without careful selection, the larger context becomes a dumping ground for noise like irrelevant notes or logs. Scaled rope expands the input range, but the system must still decide what belongs in that range to maintain effective reasoning. Scaling the positional encoding widens the model's geometry, but the inference engine still bears the cost of processing more tokens. Attention mechanisms, quantization, and serving frameworks must all support long prompts for scaling to be practical. Rope scaling is one tool in system design and requires coordination across the serving stack to maintain performance. This topic explores why simply having a larger context window in a model doesn't guarantee better recall or understanding. We'll see why more tokens don't always mean more reliable information use. Even if a model can process tens of thousands of tokens, it doesn't mean it will use all that information effectively. The model's attention mechanism has to decide what matters most, and with more tokens, important details can get lost or overshadowed by less relevant ones. Imagine a desk covered with many books. At first, having more sources helps because you have more evidence. But when the desk gets cluttered, finding the right page slows down and becomes error-prone. Models face a similar challenge. More tokens increase the chance of including the right fact, but also raise the risk of focusing on irrelevant or outdated details. Models can get distracted by irrelevant nearby text, omit key constraints in dense sequences, favor recent tokens too much, or hold on to outdated instructions. Increasing the window size alone doesn't solve these problems. Sometimes it even makes them worse by adding more confusing information. Managing context effectively is a distinct challenge from just expanding capacity. When building agents, prompts shouldn't just accumulate every past detail. Instead, they should keep what's currently important, like the task goal, recent user instructions, key tool results, and a summary of past attempts. Historical details can be retrieved when needed, separating active reasoning context from stored archives. If the system can't find the right evidence, adding more tokens won't help. Instead, it makes it harder to pick the correct snippet because it's buried among many others. Effective long context support requires retrieval ranking, prompt compression, and pruning to highlight the most relevant information. The model can't fix poor selection just by having more room. Long context capabilities can greatly impact how agents handle complex tasks. Understanding when and why to use extended context windows helps optimize performance and resource use. Long context is valuable when a task truly requires looking at many tokens at once, such as reading large documents or preserving a plan over multiple steps. However, adding more tokens increases computational cost and can dilute the model's focus. For tasks needing just a few key facts, it's often smarter to retrieve concise, high-quality information or summarize intermediate states rather than expanding the prompt unnecessarily. Just because a model can see all the details of a tool's operation doesn't mean it should process every line. Instead, keeping a concise summary of the current state in context while saving detailed logs elsewhere helps the model focus on what matters now. This approach reduces noise and makes better use of the available context window than simply trying to include everything. Long context is best saved for cases where the sequence and full detail are essential, such as legal texts or complex plans. When a task is mainly about making routing decisions or simple transformations, too much context can confuse the model by presenting too many competing pieces of information, making it harder to decide. Choosing a model isn't just about how many tokens it can handle. The right model fits the task's nature and control flow. For workloads that are short and require quick responses, a smaller model with smart routing and careful context management often beats a larger one that can read more tokens but is slower or less focused. Mixture of experts, or MO, is a way to scale models by changing how computation is allocated per token, rather than extending how far the model can see in the input sequence. Rope and context extension techniques increase the model's ability to consider longer input sequences by expanding its context window. In contrast, Mo adjusts the amount of computation devoted to each token by selectively activating parts of the model, which affects capacity rather than visibility. Imagine a dispatch center where each token is sent to one or more expert subnetworks chosen by a gating mechanism. This routing lets the model use many parameters overall, but only pay the compute cost for the selected experts at each step, enabling more specialized processing without a proportional increase in inference cost. Because Mo relies on routing tokens to experts, the quality of the gating decisions is crucial. Poor routing or uneven expert usage can reduce the benefits or cause instability. This makes Mo a system-level optimization problem, balancing expert quality and dispatcher effectiveness rather than a simple parameter increase. For agents needing to handle long documents, Mo won't extend the visible context or fixed retrieval issues. Instead, it helps when more representational capacity is required for diverse tasks. Conditional compute and context extension address different problems. One manages how much work per token, the other controls how much sequence is visible. This part covers how routing decisions, expert specialization, and load balancing work together in mixture of experts models. Understanding these elements is key to making Mo efficient and reliable. Mixture of experts models leverage specialization by letting different experts focus on distinct parts of the problem, such as syntax, domain-specific knowledge, or particular tasks. The gating network learns when to activate each expert, so each token only passes through a few experts. This sparse computation keeps efficiency high while maintaining a large overall capacity, which is especially useful for agent workloads that require broad skills without paying the cost of running all capabilities densely every time. The router is the core design element in Mo. It uses a top K gating scheme to select the most relevant experts for each token. If it's too cautious, experts won't specialize enough. If it's too unstable, tokens can jump erratically between experts, hurting coherence. Routing also affects predictability under load, since some experts may become crowded while others stay idle. This variability matters a lot in latency-sensitive systems, where rare routing paths can cause unexpected delays or missed response targets. Load balancing is crucial for Mo operation. If too many tokens go to the same expert, that expert becomes a bottleneck, while others remain unused. This isn't just inefficient, it can degrade quality because the overloaded expert acts like a dense layer, negating the benefits of sparsity. Monitoring routing distributions and expert utilization is essential. Interestingly, these issues don't show up in simple benchmarks, so a model might perform well in tests, but behave unpredictably under real traffic with varied prompts and user styles. Unlike dense models that spread knowledge evenly, Mo concentrates skills in specific experts. This can be helpful when tasks have clear subdomains, but it also creates risks if the router doesn't see the right examples or if prompts fall outside train patterns. For agents, this means prompt design and task decomposition become even more important. A supervisor agent that routes requests to specialized subagents mirrors Mo principles at a system level. The quality of routing determines whether specialization improves or harms overall performance, and bad routing can degrade the entire stack. This part explores how mixture of experts, or MO, impacts the way serving systems operate. Understanding these effects is crucial for deploying MO models effectively in real-world applications. MO models can be more efficient than dense models by activating only some experts per token, which lowers compute costs. However, this selective activation means that different inputs follow different execution paths, making latency and throughput less predictable. This variability complicates planning for system resources and meeting performance goals. Even though only a subset of experts is active at a time, the entire expert set must be available in memory, increasing the memory footprint. This trade-off means that while Mo can save compute resources, it demands more from memory and system orchestration. The overall benefit depends on whether compute or memory is the actual bottleneck in the deployment environment. Unlike dense models where every token follows a similar path, Mo models can show more variability depending on which experts are selected. This means benchmarking must include tail latency and prompt sensitivity. For production agents, it's essential to ensure that routing remains stable and consistent across the diverse tasks the model handles, not just on average performance. Adopting Mo makes sense when the system can handle its routing complexity and when total model capacity and workload diversity are priorities. It is less suitable when simplicity, predictability, or tight memory limits are critical. Mo is a targeted solution for scaling compute efficiently, not a universal fix for all model-serving challenges. Reasoning models are best understood as a type of behavior focused on deliberate thinking rather than a fundamentally new model architecture. This means their key feature is how they allocate compute to internal reasoning steps before giving an answer. These models don't rely on special transformer designs or unique attention mechanisms. Instead, they are optimized to spend more time on structured internal thinking, which helps with tasks like multi-step problem solving, planning, or sequencing tools carefully. For developers, this means reasoning is not just about the model's weights, but also about how the system manages and budgets this thinking process. Many assume reasoning models are a fixed, superior type of model, but what really matters is the amount of thinking time allowed per request. Complex tasks benefit from more deliberation, while simple ones do not need the same effort. An agent must be able to adjust the reasoning budget based on the task to be efficient and effective. This control usually appears in the chat template or request settings as a flag that turns thinking mode on or off. This flag determines whether the model engages its internal reasoning pathways for a given request. It's a runtime parameter, not a fixed property of the model itself. This example shows how a request might enable thinking mode by setting a flag in the generation parameters. The key part is the thinking true line, which tells the model to spend extra compute on internal reasoning for this request. Different platforms may use different field names, but the concept is consistent. The caller chooses whether the model should think deeply or quickly. This is crucial for agents, which might enable thinking when resolving conflicts or planning, but disable it for simple classification or data extraction tasks. The ability to control deliberation at runtime is what makes reasoning behavior flexible. Reasoning models connect to the idea of bounded autonomy because an agent must decide how much time to spend thinking before responding or asking for help. Too much thinking causes delays and higher costs, while too little risks premature answers. This trade-off makes reasoning models a bridge between scaling model capabilities and managing operational constraints. Thinking mode controls whether a model uses extra internal deliberation on a task. This part explains how thinking mode acts as a switch in the request process and why it matters for managing model behavior. Thinking mode is not about changing the model's intelligence, but about toggling whether it spends more time internally reasoning on the current task. Systems expose this switch through templates or request parameters, letting the orchestration layer decide when deeper thinking is appropriate, like during planning versus routine tasks. One simple way to enable thinking mode is by adding a flag during prompt construction. This tells the model to switch into a more deliberate mode before generating a response, which changes how the request is handled internally. This code snippet shows how a chat template can be applied with parameters to add a generation prompt and enable thinking mode. The key part is the enable_thinking flag, which triggers the model to allocate more internal reasoning resources. Thinking mode acts like changing the model's operating profile. You can send requests optimized for careful reasoning when needed or for faster, lighter responses when deliberation isn't necessary. This flexibility is crucial because different workflow steps have different demands. Turning off thinking mode saves compute when the task is straightforward or already constrained. This helps preserve resources for tasks that truly need deep reasoning. The lesson is that reasoning should be explicitly requested, not assumed by the model. Explicitly controlling thinking mode reduces confusion in complex workflows. Supervisors can route subtasks to different modes or models based on difficulty, avoiding ambiguous natural language instructions. This explicitness improves robustness and efficiency in production systems. Thinking budgets treat internal reasoning as a limited resource that a model must manage. This concept helps us control how much thought a model invests before delivering an answer, which is crucial for balancing quality and responsiveness. A thinking budget sets a clear limit on how much internal reasoning a model can perform before it must stop and respond. This is like having a fixed compute allowance or execution quota. Beyond controlling costs, it ensures the system's response time stays predictable and stops any single request from hogging resources. For autonomous agents, this predictability is just as important as the quality of the answer because it keeps the system safe and responsive. When a model has a thinking budget, it can keep reasoning as long as it has budget left. Once that budget runs out, it changes how it behaves. In practice, this often means looking for a special token that signals the budget is used up and then either continuing to reason or moving on to produce the final answer. This pseudocode shows how a system checks if reasoning is complete. If not, it tests whether the thinking budget is exhausted. If it is, the system forces a transition toward the final answer by appending a special token. Otherwise, it continues generating tokens within the remaining budget. This logic ensures the model respects its thinking limits while generating output. The system constantly monitors when the model should stop deliberating. When that moment comes, it either stops early or limits the remaining generation so the model can finish properly. This control prevents excessive delays caused by runaway reasoning, which is critical in production environments where latency spikes are unacceptable. It's important to distinguish the thinking budget from the output token budget. The output budget controls how much text the model can produce, while the thinking budget controls how much internal effort it spends before producing that text. This separation allows systems to keep reasoning short for simple tasks while reserving enough output space for concise answers, or to increase the thinking budget for harder tasks with visible cost and latency trade-offs. Thinking budgets give systems a way to balance autonomy with responsiveness. For example, a travel agent shouldn't spend unlimited time comparing options if a quick answer is expected, but it should be able to use more compute when the problem is complex. By treating deliberation as a schedulable resource, thinking budgets make this trade-off explicit and manageable, which is essential for production control. This part compares three key ways to improve a model's performance on complex tasks: extending context length, using conditional compute like mixture of experts, and allocating a reasoning budget. Understanding their differences helps us choose the right approach for specific challenges. Imagine a travel planning task where a user first requests a weekend trip, then adds constraints like budget and preferred airline. The system retrieves options and policy notes. To improve the model here, we can extend the context window to see more conversation and data, use mixture of experts to allocate compute efficiently, or increase the reasoning budget to allow deeper deliberation before making decisions. These three improvements target different layers of the model. Extending context affects what the model can see at once. Mixture of experts changes how compute is allocated conditionally, and thinking budgets control how long the model deliberates. Confusing these can lead to ineffective fixes because each addresses a distinct problem. To diagnose why a model fails, ask if it can't see enough information, can't allocate compute efficiently, or can't deliberate long enough. For example, missing user constraints suggests a visibility issue. Handling sequences slowly or expensively points to compute allocation problems. Producing shallow reasoning despite seeing evidence indicates a need for a larger thinking budget. Each cause requires a different solution. This decision tree guides which lever to apply depending on the failure mode. It separates issues of visibility, conditional compute, and deliberation. The tree helps decide whether to extend context length, route to a mixture of experts model, or increase the reasoning budget to improve performance effectively. The best practice is to make these controls explicit in the orchestration layer. The system can decide when to add more retrieved evidence, when to route to specialized models, and when to allow more deliberate reasoning. This approach keeps the architecture clear and efficient by matching the right kind of help to each stage of the task, rather than expecting the model to handle everything simultaneously. Choosing the right lever in production agent design means selecting the approach that best fits the specific workload challenges. This choice directly impacts how well the agent performs in real-world tasks. The right lever depends on the workload shape. For problems needing long sequence visibility, scaling rope or other long context methods help, but only if the prompt remains well curated. If the model is too costly across diverse tasks, mixture of experts can focus compute selectively. For careful multi-step planning, reasoning models with explicit thinking budgets work best. Each lever targets a different problem, so none should be used as a one-size-fits-all solution. Agent builders benefit from separating three key dimensions: visibility, which is how far the model can see in a sequence; work, which is the computation spent per token; and deliberation, which is the time spent before producing an answer. Rope scaling extends visibility, Mo adjusts work, and thinking budgets control deliberation. Keeping these dimensions distinct helps teams identify which factor limits their system, instead of reflexively opting for a bigger model. A practical approach is to diagnose bottlenecks in sequence. If the model can't see relevant evidence, no amount of extra thinking helps. If it sees evidence but is too slow or costly, improving compute allocation is more important than extending context length. If it's both visible and efficient but still rushed, then controlling reasoning time is key. This order prevents wasted effort and keeps optimization focused on actual limitations rather than trendy architectures. The best production agent isn't about maximizing window size, expert sparsity, or chain of thought length. Instead, it matches the model to the task shape, curates context to stay relevant, spends computation where it matters most, and limits deliberation to meet latency and cost goals. Rope, Mo, and thinking budgets each solve a part of this. The skill lies in knowing which lever to use at each stage and avoiding treating them as interchangeable signs of sophistication. Understanding how to move from individual model strengths to designing effective multi-agent teams is crucial. This part explains how model capabilities shape team architecture and performance. Token budgets are a fundamental part of designing multi-agent systems. They influence not just cost, but how the system routes tasks, manages latency, and balances quality. In multi-agent systems, every action, thinking, speaking, retrieving, or delegating, uses tokens. This means token consumption affects runtime and spending, and it becomes a key architectural consideration rather than just a billing detail. This figure illustrates how token budgets serve as a shared resource influencing how tasks are routed, how fast agents respond, the overall cost, and the quality of outputs in a multi-agent system. Token budgets should be considered alongside how tasks are divided and routed. Assigning the right model size to each subtask ensures quality without wasting tokens on unnecessary deep reasoning for simple steps. Spending too many tokens on internal thinking slows down the system, which users experience as waiting. Efficient token use improves responsiveness and throughput, especially for repetitive, consistency-driven tasks. Splitting work among agents is about distributing effort efficiently. Some agents spend more tokens on complex inference. Others stay shallow for filtering or formatting, much like power allocation in distributed systems. Choosing the right model depends on the task's characteristics. This part explains how to match model types to task demands for better system design. The best model depends on the task. Fast models suit bounded, repetitive tasks, while reasoning models handle complexity and ambiguity. Supervisors coordinate rather than solve domain problems directly. If a smaller model only yields slightly weaker summaries, a fast model suffices. But if missing trade-offs or incorrect plans result, deeper reasoning is needed. This helps justify when to invest tokens in deliberation. Search agents prioritize speed and recall. Note takers focus on reliable compression. Writers need synthesis skills, and supervisors require stable routing. Matching models to these roles improves overall team effectiveness. Tasks sensitive to latency and shallow transformations suit fast models. Tasks with ambiguity and depth need reasoning models. Supervisors coordinate both while staying lightweight, balancing responsiveness and complexity. This figure maps task characteristics to model types. Notice how latency, ambiguity, and depth form axes that guide whether to use a fast model, a reasoning model, or a supervisor for effective task handling. Benchmarks often focus on which model is strongest overall, but real systems need to consider which model fits the task, budget, and role. Smaller models can enable better system performance by freeing larger models for complex reasoning. This code defines roles with clear constraints. The search assistant focuses on quick evidence gathering without drafting. The note taker structures evidence without expanding. The writer crafts prose from outlines without new research. The supervisor manages task flow and completion. Separating the supervisor, workers, and analyst into distinct roles clarifies control flow, execution, and quality assurance within a multi-agent system. The supervisor acts as the control plane, tracking progress, deciding when to retry or hand off tasks, and determining when the overall job is done. It should avoid deep analysis or writing to maintain clear separation. Workers handle specific tasks like searching, note-taking, writing, or executing actions. Each worker knows exactly what input it accepts and what output it produces, enabling modularity and varied model classes without workflow confusion. Analysts inspect retrieved materials to assign relevant scores or filter out noise. This prevents low-quality inputs from reaching the writer and improves overall reliability without generating new content. When problems arise, knowing whether issues stem from routing, retrieval, synthesis, or verification helps isolate failures. Clear role separation keeps blame surfaces small and makes diagnosis faster and more effective. Prompt contracts define strict behavioral boundaries for each agent, preventing role drift and ensuring predictable, orchestrated team behavior. By narrowing allowed actions, prompt contracts ensure agents stick to their roles. For example, a search agent instructed not to write final prose avoids speculative synthesis, keeping the workflow moving smoothly. Models are good at improvising, but that can cause problems in coordinated systems. Restricting roles prevents agents from answering questions meant for others or producing outputs that disrupt downstream assumptions. Including instructions that forbid certain actions, like free-form writing or multiple tool calls, helps keep agents focused and prevents looping or redundant work, making the system easier to coordinate and interpret. Limiting freedom to where uncertainty is genuinely high helps agents behave consistently. This predictability makes multi-agent systems easier to operate than single models that try to do everything at once. This prompt instructs the analyst to call a specific tool once, focus on filtering evidence without generating prose, and return results only to the supervisor. It enforces strict boundaries to prevent role drift. What tools an agent can access shapes its capabilities and behavior. Treating tool binding as part of the role contract clarifies responsibilities and limits failure modes. Even if agents share the same underlying model, their behavior diverges depending on which tools they can use. This is why tool access must be carefully assigned to roles as part of their contract. Search and extraction tools broaden evidence, but risk flooding context. Outline tools reduce complexity, but may cause premature editing if misused. Assigning minimal tool sets per role keeps responsibilities clear and failures easier to diagnose. This separation creates an internal economy where each role transforms task representation appropriately. It prevents agents from overreaching and keeps the system legible as complexity grows. Giving tools only to roles that need them limits overlap, simplifies prompts, and reduces debugging complexity. This avoids anti-patterns where large models with many tools self-regulate unpredictably. This code defines role specifications linking names, tools, prompts, and model classes. It shows how each role is tailored with appropriate tools and models to fit its function within the team. Deliberation consumes tokens before producing visible output. Setting explicit thinking budgets controls how much internal exploration a reasoning agent can perform. While reasoning models handle complex subproblems well, they must have limits to prevent runaway token consumption. The budget balances intelligence with efficiency by bounding internal search. If a reasoning agent expands its chain of thought indefinitely, it may marginally improve quality but drastically reduce throughput. This also delays the supervisor's routing, slowing the whole system. Budgets act like governors, allowing more thinking on complex tasks and less on simple ones. This tuning makes costs predictable and system behavior stable across workloads. Explicit thinking budgets shape the agent team's architecture by balancing cost, quality, and stability. They are essential for scalable, efficient multi-agent systems. This code sets up three models: a fast LLM without thinking enabled, a thinker LLM with a token-based thinking budget, and a supervisor LLM. It illustrates how different models are configured for their roles. To integrate specialists into a workflow, each worker is wrapped as a graph node that normalizes output and hand control back to the supervisor. This wrapper extracts the final content from the worker's internal reasoning and packages it as a state transition. This keeps the supervisor's job simple and the system coordinated. Even well-performing workers can cause friction if their outputs are inconsistent or verbose. Wrappers enforce a stable interface, preventing such issues and simplifying routing decisions. React-style agents internally reason, call tools, and inspect results before producing concise outputs. The graph wrapper lets this complexity remain local, exposing only the final result to the supervisor. This pattern supports diverse workers with different prompts, tools, and budgets. The supervisor receives uniform updates, while workers retain autonomy, enabling flexible yet coordinated workflows. This function creates a graph, node, wrapping a React agent. It invokes the agent with the current state, extracts the last message content, and returns it as a command update routed back to the supervisor. Defining a clear roster of roles, tools, prompts, and models makes the multi-agent architecture concrete and inspectable. A roster shows how each role fits its task, what tools it can use, its prompt constraints, and which model it runs on. This makes the system understandable and easier to maintain. Users don't need to think about architecture terms. Roles simply use models suited to their tasks, like fast models for speed and reasoning models for complexity, enabling effective specialization. Explicit role definitions stop teams from defaulting to one large model for everything, which can cause cost, latency, and complexity problems. The roster keeps the team structure clear from the start. The system gathers sources, filters them through an analyst, synthesizes pros via a writer, and keeps the process moving with a supervisor. This pattern applies broadly to bounded tasks requiring disciplined output. This code builds the graph nodes by creating a React worker node for each role specification, tying together the model, tools, and prompt into composable components. Strong teams don't just produce output, they audit inputs. The analyst role filters and scores evidence to improve quality before synthesis. Retrieval often yields mixed quality evidence. By filtering early, the analyst prevents irrelevant or distracting information from degrading the final prose quality. The analyst scores help the supervisor decide if enough strong evidence exists to proceed. This tight output shape avoids ambiguity and supports efficient routing. A lightweight writer works best with screened evidence. Without filtering, writers may waste tokens reconciling conflicting inputs, lowering efficiency and quality. With a dedicated analyst, the supervisor avoids inspecting raw retrieval or blindly trusting workers. This division improves judgment and system reliability. Centralizing all tasks in one large model can create bottlenecks, increase costs, and obscure failure sources, undermining system robustness. When one model handles search, analysis, planning, drafting, and approval, it becomes expensive and slow. Diagnosing errors is harder because all responsibilities are mixed in one place. Even simple tasks must wait behind the slowest component. In contrast, specialized agents can run in parallel, improving responsiveness despite coordination overhead. Specialized roles have narrow goals, reducing coordination ambiguity. Teams can improve individual roles without disrupting others, making evolution and debugging easier. Too many agents add overhead, so work should be split only when it improves latency, quality, or role clarity. Use a single strong model for compact tasks. Use teams when bounded autonomy and budgets enhance operation. Deployment paths shape how AI models are integrated and controlled within a system. Understanding the difference between open and closed deployment is crucial for designing agents that meet operational, governance, and scalability needs. Choosing a deployment path is not just about picking a model or a hosting option separately. It's a unified decision that affects how the entire agent system operates, from data handling to policy enforcement. When building an agent, selecting the model and choosing how to deploy it are deeply connected. The deployment path defines who controls the environment where the model runs, which influences how easily the team can update prompts, enforce policies, and scale the system. For example, a managed API can quickly provide access to a powerful model, which is great for early validation. But as product needs evolve, like stricter data isolation or regional compliance, the deployment approach must support those operational demands, not just generate good text. A model that excels on benchmarks might still be unsuitable if the deployment environment is inflexible or costly. Conversely, a slightly less capable model can be ideal if it's easier to host, cheaper to run, and offers the control needed to align with product workflows. Closed deployment means the vendor manages the serving path, release schedule, and usage policies. Open deployment gives the product team ownership over model weights, serving infrastructure, and data flow. Neither is inherently better. The choice depends on whether speed or control is the priority. This figure contrasts closed deployment, where the vendor manages most operational aspects, with open deployment, which places control over serving, updates, and data boundaries in the hands of the product team. The terms open and closed are often used loosely, but they have specific operational meanings that affect how teams interact with models and infrastructure. In closed deployment, the model is accessed through a vendor-managed API. The vendor controls the weights, serving infrastructure, updates, and telemetry. Customers receive outputs, but don't control the underlying system, even if some customization is possible within vendor limits. Open deployment involves self-hosting or using providers that allow control over model weights, serving stack, scaling, and logs. The key is that the deploying team can configure and observe the runtime environment, not just access outputs. With closed paths, the provider manages updates, rate limits, and data handling. Open paths let teams align serving with agent control flow, monitor specific traces, and enforce internal policies before side effects occur. This is vital for agents that do more than generate text. They coordinate actions and state. Who owns these 5 elements determines the deployment path. Vendor ownership means less audit and governance control, while team ownership enables deeper inspection, faster iteration, and stronger compliance. The question is not only which model is best, but who controls the system that delivers it. Deployment paths influence how quickly teams can innovate and how accessible models are throughout the product lifecycle. Managed APIs remove infrastructure hurdles, letting teams quickly test if the agent can perform key tasks. This fast feedback between product, UX, and policy helps decide if the problem is worth solving before investing heavily in infrastructure. Having instant access to frontier models through hosted APIs can be decisive during discovery phases. However, restrictions like regional limits or rate caps can make an excellent model inaccessible where or when the product needs it. Open models benefit from community-driven releases, tooling, and deployment options. This flexibility lets teams start hosted, then migrate to internal deployments or swap inference backends without changing core logic, increasing long-term accessibility. Closed managed access speeds early experimentation, while open ecosystems support adaptation and control once requirements are clearer. Teams choose deployment paths based on current constraints, not ideology. Balancing speed and control is needed. Control over deployment enables deeper customization of agent behavior beyond prompt tuning, affecting tool use, uncertainty handling, and policy adherence. Owning the model and serving environment lets teams shape behavior through prompt design, adapters, routing, and even changes to the serving stack. This is critical for agents that must coordinate complex workflows and respect operational constraints. While closed systems permit some customization via instructions or structured outputs, the runtime environment remains controlled by the vendor. This limits how closely the agent can be aligned with specific latency, fallback, or logging requirements. Managed models may change unexpectedly as providers update them, which can disrupt agents needing stable behavior. Open deployment lets teams pin versions, test releases, and control rollouts to maintain consistent operation. Open deployment demands operational maturity. Teams must manage runtime quality, security, monitoring, and versioning. Without this discipline, the freedom to customize can lead to fragility rather than strength. Choosing a model based solely on benchmark rankings overlooks practical needs like latency, cost, and reliability. The best model for an agent depends on how well it fits the specific workload and constraints. A model that scores highest on benchmarks may be too slow, expensive, or inflexible for interactive agents. What matters is sufficient reasoning, policy adherence, and tool discipline within the agent's operational context. For example, an open model that meets reasoning and control needs while being cheaper and easier to host may outperform a top-ranked model that is costly or rigid. The question is which model performs best under real-world constraints. Techniques like prompt engineering, routing, tool integration, and retrieval can elevate a good enough model into a practical agent component. Performance is a portfolio of capabilities rather than a single score. Highly capable models can introduce unwanted flexibility that complicates control. Sometimes a smaller, specialized model delivers more reliable, repeatable behavior, which is crucial for production agents. Cost considerations go beyond per-request pricing. Understanding the full operational burden and scaling economics is essential for choosing the right deployment path. During prototyping, paying only for what is used is efficient and elegant. This avoids upfront infrastructure costs while traffic is low and requirements are still forming. Agents often make multiple model calls per interaction, increasing token costs. At scale, self-hosting open models can offer better unit economics by utilizing hardware more efficiently. Beyond hardware, teams must invest in deployment automation, monitoring, incident response, and maintenance. These distributed costs affect total cost of ownership and can outweigh per-request savings. Managed services offer speed and elasticity, while self-hosting offers control and lower marginal cost at scale. The choice depends on workload predictability and growth, with flexibility to switch paths as needs evolve. Governance requirements often dictate deployment choices, especially when handling sensitive or regulated data. Knowing exactly where data is processed, who accesses logs, and how retention is managed is critical in regulated environments. A technically strong model that fails these requirements may be unusable. Deploying models on private infrastructure lets teams keep sensitive data in-house, instrument detailed traces, and meet compliance standards for residency and retention, which is vital for regulated workflows. Using a hosted model relies on vendor assurances and policies. While this reduces infrastructure burden, it introduces risks if service policies change or regional availability fluctuates, potentially forcing application changes. Lock-in can arise from proprietary prompts, tool integrations, logging defaults, and rate limits. Open deployment reduces this risk by enabling workload portability and preserving governance control as products mature. Choosing a deployment path should start with clear priorities: speed, control, compliance, or cost. Identifying the binding constraint guides the right choice. If proving product value quickly is key, closed managed services are often best. For deep customization or regulatory needs, open deployment is more suitable. Avoid choosing based on abstract preferences instead of workload realities. This figure illustrates how deployment decisions align with binding constraints like speed or control, and how hybrid strategies can maintain flexibility over time. Real-time agents require predictable latency, favoring deployments that optimize response times. Bursty prototypes benefit from managed elasticity, while steady high-volume apps may justify self-hosting. Sensitive data heightens the value of control. Teams needing tight behavioral contracts prefer ownership for end-to-end control. However, operational maturity is essential. Without it, self-hosting can become a liability rather than an advantage. Ask what the team needs: data sovereignty, load elasticity, policy isolation, fast iteration, or cost efficiency. The deployment path follows from these needs, often combining closed and open approaches over time. A pragmatic approach starts with managed services for speed and learning, then selectively moves to open deployment for control and cost optimization as the product matures. Early in development, focus on speed and feedback by using hosted models to test if the agent can perform essential tasks reliably and gain user trust before investing in infrastructure. After validation, move high-cost or sensitive components to self-hosted environments for better control and cost efficiency, while less critical functions may remain hosted until it makes operational sense to migrate them. This approach avoids premature commitments and helps teams focus on the true bottlenecks, whether they lie in hosting, prompt design, or tool reliability. It acts as both an exit strategy from vendor lock-in and an on-ramp to greater control. The best deployment path preserves options while meeting current constraints. This flexibility often determines whether an agent remains a prototype or evolves into a scalable, governed product. This topic explores practical techniques to optimize large open-source models. We'll cover methods that reduce training costs, improve efficiency, and enable easier deployment without sacrificing performance. Optimization is often seen as just reducing training costs, but it plays a bigger role in deployment. We'll explore why making models efficient in real-world systems requires balancing multiple constraints beyond training alone. Open model optimization is more complex than just shrinking training expenses. In agent systems, models are called repeatedly within control loops that include branching, retries, and human interactions. So, the challenge is not only teaching the model a task, but ensuring it operates efficiently under latency, memory, and cost limits during deployment. There are two distinct optimization goals. One changes the model's parameters to specialize it for a task or domain. The other keeps the model's behavior the same, but makes inference faster or cheaper. Techniques like parameter-efficient fine-tuning focus on specialization, while quantization and serving improvements focus on delivery. Both are needed in production, but they address different bottlenecks. A helpful analogy is to think of the base model as an engine. PFD modules act like attachments that change how the engine performs specific jobs. Quantization and serving infrastructure are like the fuel system and transmission, determining how efficiently the engine runs. If the model struggles to understand a domain, speeding it up won't help. If it fits the task, but not the hardware, specialization alone won't solve deployment challenges. This diagram breaks down the optimization stack into three parts. PFD modules adjust the model's behavior to specialize it. Quantization reduces memory usage and cost by compressing the model. The serving infrastructure manages how models are delivered efficiently in production environments. Each layer tackles a different aspect of making models practical at scale. Consider a travel assistant needing different model variants for itinerary drafting, policy-sensitive booking, and cautious approval handling. Fully fine-tuned separate models for each variant can become too costly. Using a shared base model with lightweight specialization keeps a stable core while customizing only what's necessary. The goal is to reduce the real constraints blocking deployment, not just improve abstract model quality. Parameter-efficient fine-tuning, or PFT, is a key approach for adapting large pre-trained models by modifying only a small portion of their parameters or adding a few trainable components while keeping the main model frozen. This method allows us to specialize models efficiently without retraining everything from scratch. Instead of retraining the entire model, PFT keeps the core representation intact and focuses on learning only the adjustments needed for a specific task. This makes it especially useful for agent systems that require domain specialization or specific behaviors without losing the general capabilities of the base model. By updating only a small subset of parameters, training becomes more efficient in terms of memory and compute. This efficiency allows teams to experiment more, work within smaller budgets, and maintain a stable base model that supports many different downstream uses without duplication or complex forks. Unlike full fine-tuning, where the entire model is replaced, PFD lets you version the base model independently from the specialized adaptations. This separation makes it easier to update specific behaviors quickly, such as changing a policy or output style, without retraining or replacing the whole model. Prompt engineering can steer model behavior, but it doesn't alter what the model has learned internally. PFD modifies the model's representations themselves, which is important for consistent, scalable tasks and durable behavior across sessions and deployments. This durability often makes PFD the first step when a base model needs more precise specialization. This part explains how parameter-efficient fine-tuning, or PFT, lowers both the risks and expenses involved in adapting large models compared to full fine-tuning. Full fine-tuning adjusts every parameter in the model, which can cause the model to lose some of its original abilities. This phenomenon is called catastrophic forgetting, where the model becomes very good at a narrow task, but less reliable on others. In systems that perform many roles, this loss can reduce overall reliability, even if training time is saved. PFD keeps the base model mostly unchanged and only learns a small set of additional parameters or corrective layers. This limits how much the original capabilities are disturbed, making it safer to experiment. If the new adaptation doesn't work well, it's easier to revert because the core model remains intact, and successful adaptations become reusable components. Large organizations often face challenges when they create a fully fine-tuned model for each task, leading to many versions that are costly to store and manage. PFT changes this by keeping a few base models and adding small, lightweight parameter updates for each specialization. This approach cuts storage needs, speeds up training, and simplifies deployment and maintenance. When adapting models is inexpensive, teams can create distinct specializations for different tasks instead of forcing multiple roles into one model. For example, one specialization might handle research while another manages safety checks. This separation avoids mixing behaviors that should remain independent, improving architecture and reducing unexpected interactions. LoRa applies low-rank updates to frozen model weights, creating a compact and efficient way to adapt large models without changing their core parameters. Instead of modifying the original weight matrix, LoRa trains two small matrices. Their product acts as a correction added to the frozen weights. This keeps the base model intact while steering it toward a new task with a minimal, manageable adjustment. Operationally, LoRa behaves like a slim correction layer inserted into the model. The original model provides broad language skills, while the low-rank update gently shifts its behavior toward a specific domain or style. This reduces training memory and allows distributing small adapters instead of full models. Because the base weights remain frozen, LoRa adapters act like patches rather than full model replacements. This simplifies tracking changes, rolling back updates, and selectively applying adapters. It also allows a single base model to serve multiple tasks by swapping adapters, which is more efficient for shared hardware environments. Teams can keep one common base model and share only the small adapter weights for each specialization. This lowers storage and synchronization demands. LoRa thus changes the economics of model specialization, enabling flexible combinations of base capabilities with different tools or policies without heavy duplication. This part explains when LoRa is an effective adaptation method and when it falls short. Understanding these boundaries helps decide if LoRa suits a particular model tuning task or if other approaches are needed. LoRa excels when the base model already performs most of the desired tasks well, and the remaining gap is about fine-tuning details like tone, vocabulary, or specific response formats. In such cases, LoRa can efficiently nudge the model's behavior without retraining everything, making it a cost-effective way to specialize a broadly capable model. If the base model doesn't have the necessary reasoning, context understanding, or reliability, then applying LoRa won't transform it into a better system. This is a common mistake, expecting LoRa to compensate for a poor model task fit. LoRa can refine a strong foundation, but can't repair fundamental weaknesses in the base model itself. When an application demands major shifts in behavior across many capabilities or needs a standalone model without dependencies, LoRa may not be the best approach. Such deep changes require more extensive retraining, which is costlier and harder to manage. LoRa shines when you want targeted, stable specialization without losing the base model's broad strengths. A practical way to decide is to ask what kind of problem you face. If you need domain-specific phrasing or modest tuning, LoRa fits well. But if latency, memory, or fundamental model weakness is the issue, LoRa won't solve it. It can sharpen how the model expresses itself, but can't fix the base model's fundamental abilities. Adapters provide a way to customize a model for specific tasks by adding small, separate modules. This approach keeps the main model intact while allowing targeted updates, which makes managing different task versions simpler. Instead of changing the main model's weights directly, adapters add small trainable components inside the network. These modules are usually placed between or alongside transformer layers and are trained specifically for the target task, leaving the original model mostly unchanged. This separation means adapters are easier to treat as independent task modules. Teams can clearly see which parts handle specialization, making it simpler to organize, assign responsibility, and manage these modules as optional capabilities rather than mixing everything into one monolithic model. When a single base model supports multiple workflows, keeping specializations as separate adapters prevents changes in one area from affecting others. This modularity improves clarity in testing, release schedules, and ownership beyond just saving memory or compute resources. Adapters fit well when many task variants need to coexist but remain distinct. They allow the base model to stay common infrastructure while encoding different needs in separate modules. This approach supports reuse and keeps the system easier to understand and less fragile. LoRa and adapters are two popular methods for specializing large models efficiently. Understanding their differences helps decide which fits best for a particular deployment or workflow. LoRa focuses on creating small, efficient adjustments to the existing model weights using low-rank updates. This keeps the changes lightweight and easy to distribute. Adapters, on the other hand, add separate modules that clearly separate the base model from task-specific components, making the specialization more modular. When deploying, LoRa works well as an overlay on a common backbone model, especially if many similar variants are needed. It's great for small behavior tweaks without changing the core. Adapters fit better when you want clear task modules that can be managed independently, like plugins that you can swap in and out. In terms of memory, LoRa keeps the trainable parameters very small, which is useful when resources are tight. Adapters introduce some extra structure, but that helps keep task boundaries clear. This clarity can simplify managing multiple tasks and routing requests in multi-tenant systems. A helpful way to decide is to ask whether the main challenge is representing changes efficiently or managing many specialized modules. LoRa excels when you want compact representation, while adapters shine when you need modular portfolio management. Neither replaces the need for a strong base model, but both help tailor behavior without rebuilding from scratch. This part covers how adapting pre-trained models can cause them to forget previous skills, how we can reuse models efficiently, and why specialization matters economically in model deployment. When a model is retrained aggressively on new data, it can lose important abilities it had before. This is especially risky for agents that need to perform multiple tasks like summarizing evidence, following instructions, or handling tool outputs. Losing any of these can reduce overall reliability despite gains in a specific domain. Parameter-efficient fine-tuning, or PFT, helps avoid catastrophic forgetting by preserving the original model's behavior. Instead of retraining the whole model, it adds small specialized layers. This lets us keep a strong general-purpose core and add multiple task-specific extensions without losing prior skills. When different teams work on related tasks, like travel planning or support, they don't need separate full models. Instead, they can share a common foundation and add controlled specializations. This reduces duplication, lowers training costs, and keeps the organization's models manageable. Specialization isn't just about better performance on a task. It also means maintaining models sustainably. PFT enables incremental evolution where shared base supports many small, manageable variants. This approach makes deploying open models practical by avoiding the cost of maintaining many full checkpoints. Quantization is a key technique that helps reduce the memory footprint and computational cost of running large models. Understanding how it works and why it matters is essential for deploying models efficiently. Unlike parameter-efficient fine-tuning, which changes how the model behaves, quantization changes how the model is represented internally. By converting weights to lower precision formats like 8-bit or 4-bit, The model takes up less space and often runs faster during inference. This compression is crucial for making large models practical to deploy, especially in open environments. Reducing precision shrinks the size of each weight, which lowers GPU memory demands and speeds up loading times. This often improves throughput because moving data through memory can be a bigger bottleneck than raw computation. If a model is too large for a device, it might need slower memory or more expensive hardware. Quantization can shift these limits, enabling more efficient deployment. In agent applications, models often run repeatedly in a session, occupying hardware for long periods. Shrinking the model's memory footprint through quantization frees up resources for other tasks like caching and handling multiple requests simultaneously. This makes quantization more than just compression. It's a tool for managing capacity and enabling more flexible serving setups. It's important to remember that quantization doesn't make a weak model better. It only lowers the cost of using a model that already works well for the task. If the base model isn't suitable, compressing it won't solve that problem. Quantization should be seen as a deployment enabler, not a way to boost model performance or fix fundamental issues. Quantization offers benefits like smaller models and faster inference, but it also introduces important trade-offs. We need to understand how these trade-offs affect model quality, compatibility with hardware and software, and practical limits on deployment. Lowering precision through quantization can reduce the quality of model outputs. Some tasks handle this well, especially if the model is already strong and efficiency is a priority. But tasks that require careful reasoning or subtle distinctions may suffer more, so the trade-off between quality and efficiency must be clear. Not all quantization formats work equally well everywhere. Some look good in theory, but cause problems in specific deployment environments. The choice involves more than just bit width. It depends on whether the runtime supports the format reliably and whether the tooling integrates smoothly. While quantization reduces memory usage and cost, it can also change how you serve models. Higher concurrency might be possible, but managing many model variants or adapters can add complexity. Quantization solves some resource problems, but may reveal others, so it should be applied thoughtfully where it truly helps. A common mistake is to rely on quantization to fix a model that doesn't suit the task well. First, ensure the model meets the workload requirements. Then consider memory and cost constraints. Only after that should you apply quantization. It can make deployment feasible, but can't replace a model that lacks the right capabilities. This part covers the practical tools and workflows that make deploying open models more efficient. Understanding these tools helps us bridge the gap between theoretical model design and real-world deployment challenges. Tools such as Bit and Unsloth simplify complex processes like quantization and model adaptation. They don't change the fundamental trade-offs in model design, but they make applying those trade-offs much easier by reducing manual work and speeding up the path from experimentation to deployment. These tools solve the crucial problem of linking model adaptation with serving infrastructure. When a team wants a quantized base model combined with lightweight specializations, the tooling ecosystem often makes that combination feasible to deploy and maintain. Without this support, many deployment strategies remain theoretically sound but practically difficult to manage. It's important to separate tooling from architectural design. Tools can make certain formats easier to train or run, but they don't eliminate the fundamental differences between specialization and acceleration. This distinction ensures that teams use tools to support thoughtful design choices rather than substituting tools for good judgment about what fits production constraints best. This part explores how to efficiently serve multiple specialized versions of a model on the same hardware. It focuses on the challenges and strategies for managing many variants without wasting resources. When an organization adopts parameter-efficient fine-tuning seriously, the deployment problem changes. Instead of one model handling one task, you often have many specialized versions derived from the same base model. Assigning a separate GPU to each variant quickly becomes costly and inefficient, leading to wasted capacity and higher operational complexity. This challenge is most apparent in customer-facing systems where various teams or request types need different behaviors. For example, A support platform might use separate specializations for billing or troubleshooting, while a travel assistant might have distinct modes for research or booking. Though the base model is the same, each variant tailors the final behavior to its specific use case. The key question becomes how to place these specializations on hardware so that memory pressure, cache thrashing, and idle GPUs don't negate the benefits of specialization. This means serving architecture must be part of the overall optimization, alongside adaptation methods and scheduling policies. Without a strong serving strategy, even well-trained specializations can be costly to deploy. LoRaX demonstrates a practical way to organize multi-adapter serving in production environments. Understanding its architecture helps clarify how to efficiently manage multiple model variants on shared hardware. LoRaX keeps the main model shared, while loading LoRa adapters only when necessary. It batches requests that use the same adapters on one machine, which reduces memory use and supports many task-specific variants without dedicating a GPU to each one. This pattern balances two facts. Specialized behavior is important for different tasks, but the specialized parts are much smaller than the main model. By treating the base model as a shared foundation and swapping adapters in and out, teams can manage many behaviors without the cost of duplicating the entire model. When requests need different adapters, a scheduler can keep the main model loaded while swapping only the smaller adapters in and out. This approach avoids redundant memory use and lets one machine serve many specialized tasks efficiently, unlike deploying full separate models for each variant. LoRaX differs from LoRa itself. LoRa is the method to adapt models, while LoRaX is the system for serving many such adaptations efficiently. Teams with only a few variants might use LoRa without LoRaX, but when many small specializations are needed, LoRaX offers a more economical way to deploy them on shared hardware. These three techniques enable efficient deployment of many specialized model adapters simultaneously. They address memory limits, latency, and throughput challenges in serving multiple adapted models. Dynamic adapter loading means the system loads adapter weights only when they are required for a request, instead of keeping all adapters in memory all the time. This approach reduces the memory burden on the GPU and allows hosting many more adapter variants than would otherwise fit. It's essential because adapter counts can grow faster than available hardware resources, and keeping all adapters loaded would negate the efficiency benefits of parameter-efficient fine-tuning. Tiered caching organizes adapter weights into multiple levels of storage based on how often they are used. The most frequently accessed weights stay in the fastest GPU memory. Less used ones move to CPU memory, and rarely used weights remain on disk. This hierarchy balances speed and capacity, preventing memory overload, while keeping the most important data quickly accessible. Managing this cache carefully is critical to avoid latency spikes and maintain smooth performance. Continuous multi-adapter batching increases efficiency by combining requests for different adapters into a single batch when possible. Instead of waiting to accumulate many requests for the same adapter, the system merges diverse requests to keep the hardware fully utilized. This reduces tail latency and improves throughput, especially when demand is spread thinly across many specialized adapters in a shared service environment. These three mechanisms together enable multi-adapter systems to operate efficiently at scale. Without them, the system might be theoretically sound, but impractical due to memory limits and latency issues. By dynamically managing weights and intelligently batching requests, the serving layer makes specialization affordable and usable in real-world deployments. The full efficiency of adaptive models depends on integrating these techniques into the request scheduler and weight manager. Combining multiple optimization techniques creates a more effective and practical model deployment. This part explains how base models, PFD layers, quantization, and serving strategies work together to meet real-world constraints. Deployments rarely rely on just one optimization method. A base model provides general language understanding, while PFD layers add task-specific skills without retraining everything. Quantization shrinks the model to save memory and cost, and serving layers manage how these specialized models run efficiently on hardware. This figure illustrates how different constraints guide optimization choices. If the model doesn't fit the task well, you improve the base or add PFT. Memory limits suggest quantization. Handling many task variants on shared hardware requires adapter-aware serving. These methods often combine to address multiple constraints simultaneously. When facing a production challenge, identify the bottleneck clearly. If the task demands better understanding, improve the base model or use PFT. If memory is tight, quantize the weights. If you need to serve many specialized models efficiently, adapter-aware serving is the solution. Each technique targets a specific constraint. For example, an Atlas-style agent starts with a powerful general base model, adds a small LoRa module for travel planning and policy phrasing, compresses the backbone with quantization to fit hardware, and serves multiple task variants through a multi-adapter runtime. This approach extends and compresses the brain without replacing it, managing specialization and resource use effectively. The key is to distinguish between what changes the model's behavior, what changes its size, and what changes how it's delivered. PFT adjusts the brain's knowledge, quantization shrinks its memory footprint, and serving manages how it runs and shares resources. This separation makes it easier to pick the right combination for better task fit, smaller models, or faster response times. This topic focuses on how to choose the right models for intelligent agents, how to scale them effectively, and how to tailor them for specific tasks. Understanding these steps is essential to building agents that perform well and adapt to varied environments. Choosing a model for an agent is not just about picking the best performing one. Instead, it involves considering how the model fits into the entire system, including inference methods and deployment conditions. By the time you select a model, the question shifts from which model is best in isolation to which model works well with the inference strategy and deployment setup without making the system fragile. Agents are dynamic systems with state, tool use, and recovery mechanisms, so a model that looks good on a benchmark might still cause problems if it's expensive, slow, or hard to control within a larger system. Once an agent like Atlas Travel Assistant moves beyond prototype, its tasks split into many subproblems such as classification, planning, and tool selection. Each subproblem might need a different model family. Treating the model as a single block misses the benefits of combining smaller models with caching, routing, and approval mechanisms. This system-wide view often lets smaller, well-used models outperform larger, indiscriminate ones. Choosing a model is about balancing capability with controllability and serving complexity. Decoder-only generators suit incremental actions and tool calls, while reasoning models help with uncertainty and dependencies. Open models offer control over data and latency, but require more operational effort. No single model is best universally. The choice depends on task demands, budget, and governance. Focus on what the agent spends most of its time doing. For routine tasks, the smallest model that meets quality is best. For complex planning or ambiguity, stronger reasoning models are needed, but only where they help. When customization or control is critical, open models become attractive despite operational costs. The best model fits the job once all downstream effects are considered. Choosing the right model family depends on the shape of the workload, not just the model's prestige. This approach helps match tasks to the models best suited for them. Tasks like drafting quick replies or extracting structured data benefit from models that respond fast and reliably. These tasks don't need deep thinking but require low latency and system simplicity to handle repeated calls efficiently. When tasks involve trade-offs and uncertainty, such as long-form trip planning, models that can deliberate and analyze multiple options add real value. They spend more time decomposing problems and checking assumptions, which is worthwhile only when the task demands deeper reasoning. In workloads where the model interprets and synthesizes retrieved data, success depends on both the retrieval system and the model's ability to integrate that information correctly. Encoder-only models often handle understanding and filtering efficiently, supporting the overall system by deciding what content should enter the generator's context. Decoder-only models are best for continuing conversations or iterative tasks. Encoder-only models excel at inspecting and retrieving information. Reasoning-oriented models handle complex searches. Mixture of experts models allocate capacity selectively for broad workloads. Open models allow adaptation to specific data or policies. Different parts of a system may use different families for their unique strengths. This figure illustrates how different model families align with specific workload shapes. Generation tasks favor decoder-only models. Retrieval tasks suit encoder-only models. Planning benefits from reasoning-oriented models. Conditional compute leverages mixture of experts. And specialization uses open models adapted to particular needs. Using one large model for all tasks often wastes resources and reduces control. For example, expensive reasoning models may be overkill for simple retrieval tasks, and routing all requests to a large model can slow down trivial cases. It's more efficient to assign the smallest suitable model family to each part of the workflow, reserving larger models only where the task truly requires them. Choosing the smallest model that reliably meets your quality needs is essential for building efficient and manageable systems. This approach balances performance with cost and operational simplicity. Reliability here means the model performs well enough to keep error rates low so that any mistakes can be handled through recovery or human review. A smaller, mostly correct model that's cheap to run and retry can outperform a larger, slightly better model that is costly and slow. Many workflows have stages where errors vary in impact. For example, a fast, small model might occasionally misroute an intent, but that's okay if the next step can fix it. However, for critical final steps like bookings, errors are costly and require stronger models or controls. Using a large model too soon can hide problems like poor retrieval or weak state management. A smaller model forces the system to clarify where accuracy depends on design rather than model power. Relying on a model's extra capacity can create fragile architectures. Begin by defining what quality the model must achieve, then identify the least expensive model that meets this in realistic scenarios. Real workloads involve complex interactions and states, so a model that works well alone might fail in production. When errors are cheap, smaller models with some mistakes can work if validation cleans up errors. But when errors are costly, it's safer to pick a more capable model even if it's underused. The best model is the one that consistently meets your acceptance criteria, not just the most powerful on average. This topic covers how three key factors, context length, cached state, and inference time computation, interact to affect the performance and cost of agent systems. Understanding these relationships helps manage resources effectively during runtime. The choice of model is no longer just about quality. Runtime factors play a crucial role. Longer contexts require more memory and slow down generation. A larger key-value cache helps avoid recomputation but increases memory use. More thinking time can improve decisions but adds latency and raises costs, especially with longer contexts. Reusing attention through caching saves time by avoiding repeated calculations each turn, but requires storing keys and values, which consumes memory. In agents, this trade-off becomes clear because each new observation or action adds to the working set, making the model heavier to run as the interaction grows longer. When a model deliberates extensively over a large context, it pays twice, once for the existing tokens in scope and again for the extra tokens generated during thinking. Longer context windows aren't inherently better. They increase cost and can reduce accuracy if irrelevant information distracts the model's attention. Separating active working context from archival state helps control cache growth. The model should focus only on what's immediately needed for the next step, while less urgent information moves to retrievable storage or summaries. This distinction is key to effective context management beyond just prompt length. The most efficient system isn't always the one with the longest context or deepest reasoning. Throughput and memory use depend on both generation strategy and state size. Good cache behavior can be undone by bloated prompts, and large contexts can underperform if they contain stale data. Designing agents means allocating budgets wisely to maximize accuracy, not just impress with scale. Understanding when to invest extra thinking time is crucial. This part explains how deliberation can improve decisions in complex tasks and when it simply wastes resources. Reasoning-oriented models are designed to use more computational effort when a problem demands it. Many tasks aren't solved in a single step because they involve unclear instructions, hidden rules, or complex trade-offs. In these cases, spending more time thinking helps avoid jumping to conclusions too quickly. For example, a travel agent weighing flights, fare rules, and user preferences benefits from careful deliberation because the best choice isn't obvious immediately. However, thinking longer doesn't guarantee better results. Deliberation becomes wasteful when the task is straightforward, mostly mechanical, or when external checks already catch errors. For instance, if a tool gives a deterministic answer, spending extra time recomputing it is unnecessary. Similarly, if a retrieval system narrows options down to a few clear choices, the model should focus on comparing those rather than inventing new possibilities. The goal is to use thinking to handle uncertainty, not to overcomplicate every answer. Thinking budgets are operational controls, not magical model features. The same model can run conservatively for routine tasks and more expansively for risky or high-impact ones. The system should decide when to spend extra time based on how risky or uncertain the task is. For example, a low-stakes draft with small uncertainty might need no extra thought, while a booking decision visible to users with moderate uncertainty deserves careful internal search. The model's ability to think longer is valuable only when the workflow knows when to request that effort. A related risk is that reasoning models can seem more competent because their outputs are more fluent, even if the decisions aren't actually better. This can be dangerous in agent systems where polished answers mask weak grounding. The best practice is to combine deliberation with clear acceptance criteria. If the model thinks longer, it should be because the system expects higher reliability on certain decisions, not just because the output sounds more sophisticated. Each extra token of thought should justify itself by reducing failure risk more than it adds cost or delay. This part explains how assigning specific roles to different models in a multi-agent system can improve overall performance. We'll see how matching tasks to models based on their strengths creates more efficient and reliable systems. Instead of expecting a single model to handle every part of a task, multi-agent systems divide work by assigning roles. For example, one model might quickly draft responses, while another plans or verifies quality. This approach lowers costs and makes the system more predictable by not relying on one model to be perfect at everything. In the Pulse Support Orchestrator, a fast model classifies requests and drafts initial replies. Another component retrieves relevant information, while specialists handle complex cases like billing. A supervisor decides when to escalate or involve humans. The supervisor isn't necessarily the most powerful model, but manages routing responsibly, ensuring each role fits the intelligence it needs. Atlas applies the same principle by having a lightweight generator suggest options quickly. A stronger planner balances constraints and preferences, while specialists focus on fair rules or visa restrictions. Finally, a verifier checks that everything meets user and organizational requirements. This division limits errors and improves robustness compared to a single model handling everything. Role specialization works best when each model's responsibilities are clearly defined. If a generator tries to make final policy decisions, or a retrieval specialist attempts broad narrative tasks, confusion and mistakes arise. Clear boundaries reduce duplicated effort and prevent errors from bouncing between components, ensuring each part is accountable for its output. Adding more roles means more complexity in routing and managing state. A multi-agent system outperforms a single model only if the benefits of specialization outweigh this overhead. Roles should reflect genuine differences in workload, such as speed, uncertainty, or correctness needs. Avoid building a team just because it's possible. Build it because the task demands it. Deployment paths define how a model is integrated and operated within an organization. Understanding these options is crucial because they affect control, cost, privacy, and operational complexity. Choosing how to deploy a model is more than picking the best performing one. It involves governance decisions about privacy exposure, cost predictability, latency, and how much control you want over customization and operations. Closed, vendor-hosted models reduce infrastructure work, but create dependencies on external policies and pricing. Open, self-hosted models give more control, but require managing serving and scaling internally. Hybrid approaches mix these to balance convenience and control. The best deployment path depends on factors beyond raw model performance. If your workflow handles sensitive data or has strict compliance needs, controlling data flow is critical. For bursty workloads, hosted models simplify operations by avoiding the need to handle peak capacity yourself. For steady workloads sensitive to latency or cost, self-hosting can be more efficient because you can optimize for your specific traffic patterns. Deployment decisions influence the entire system architecture. Hosted models reduce infrastructure responsibilities but limit control over versioning and safety features. Self-hosting increases control but adds burdens like monitoring and recovery. Hybrid systems offer flexibility but require complex routing and testing. These differences directly impact the reliability of agent systems, where failures or timeouts can disrupt the whole operation. Focusing only on benchmark scores can lead to poor deployment decisions. A model with the highest score may not fit your environment if the operational demands are mismatched. The real question is which deployment arrangement lets your organization deliver acceptable quality while managing risk and operational effort. This broader perspective is essential for building effective agent systems. Specializing open models lets teams adapt a base model to their specific needs without starting from scratch. This approach is crucial for practical deployment, especially when full retraining is costly or unnecessary. Once a team commits to using an open or self-hosted model, they can specialize at using parameter-efficient fine-tuning methods. These techniques adjust the model's behavior for specific tasks or policies without the expense of retraining the entire model, which is rarely justified for agent workloads. Approaches like LoRa and adapters add modular layers that change model behavior with few trainable parameters. This modularity allows teams to attach, update, or roll back task-specific changes without disrupting the base model, which is especially useful when different roles require different model variants. It's important to distinguish between adapting a model's behavior and making it serving more efficient. Fine-tuning changes what the model does, while compression and optimization improve how quickly and cheaply it can do it. Effective production systems often combine both to align behavior and reduce inference costs. Using parameter-efficient methods limits the impact of changes, making it easier to swap or update specialized layers as tasks or policies evolve. This flexibility is vital for agent systems, which frequently change tools, workflows, and rules, making these techniques valuable operational tools beyond just machine learning. This topic explores how quantization and serving optimizations make deploying models in production more practical and efficient. Understanding these techniques helps balance model performance with real-world constraints like cost and latency. Quantization works by lowering the numerical precision of model parameters, which cuts down memory usage and often speeds up processing. This can make a model that was too costly or hardware-intensive to serve suddenly feasible on more common devices. However, this efficiency comes at the cost of some loss in how accurately the model represents information. When using quantized models in agent systems, it's important to judge the impact on the agent's overall performance, not just isolated metrics like perplexity. A quantized model might perform well on routine tasks and be ideal for high-volume use, but could struggle with complex or rare cases. The real question is whether the gains in efficiency outweigh any loss in quality for the tasks the agent actually needs to do. Effective serving frameworks and optimization tools turn these model efficiency strategies into practical workflows. They allow teams to package model weights, apply compression, batch requests, manage caching, and scale replicas seamlessly. This makes optimization a routine part of infrastructure rather than a one-time research effort, which is crucial because agents must keep running reliably as the product evolves. Optimization should be considered part of selecting a model, not something done afterward. Sometimes a slightly less accurate model that compresses or adapts well will serve better in production than a stronger but harder to optimize model. In agent systems, the ability to deploy a model reliably and cost-effectively is a core capability. Without that, even the best model on paper isn't truly usable. This part examines the hidden costs that come with increasing model sophistication. We'll explore how coordination, controllability, and serving complexity impact system design beyond raw capability. Focusing only on improving a model's capability often overlooks the extra costs it imposes on the system. A stronger model might reduce errors, but it can also increase the complexity of managing and deploying it. This can lead to higher latency, greater expense, and fragile compensations for weak system design. Controllability refers to how easily we can bound or constrain a model's behavior, especially when strict outputs or policies are needed. Serving complexity involves the demands a model places on hardware and deployment. Coordination cost arises in multi-agent setups where richer outputs can make supervision more difficult. Each of these adds layers of hidden overhead. Systems often improve more by simplifying operations than by pushing for the most capable model. A smaller, well-structured model with clear roles and strong retrieval can outperform a complex monolith that's hard to monitor and expensive to run. Capability remains important, but it must be balanced against the costs of control and deployment. There's a fundamental trade-off between capability, controllability, and serving efficiency. Increasing one often raises costs or reduces flexibility in another. Good architecture finds a balance that fits the business needs and workload, rather than maximizing any single dimension. This figure illustrates the three-way trade-off in agent model strategy. Notice how capability, controllability, and serving efficiency form a triangle, showing that improving one affects the others. Robust systems find a middle ground that balances these factors to maintain performance and manageability. This framework helps us systematically evaluate architecture choices by focusing on key decision points. It guides how to select and configure models based on the task and operational constraints. We begin by clearly defining what the agent needs to do, whether it's drafting text, classifying data, planning steps, retrieving information, verifying facts, or acting under constraints. This definition points us to the most suitable model type. For example, generation tasks with structured control often use decoder-only models, while evidence-driven tasks benefit from encoder components. Tasks involving ambiguity or complex trade-offs may require reasoning-oriented models. When possible, splitting tasks into specialized roles improves performance over a single model trying to do everything. Next, we decide how much thinking the task deserves by considering the consequences of failure. If the task happens often but carries low risk, a smaller, faster model that meets the accuracy bar is best. For rare but high-stakes tasks, investing in a more capable model or longer processing time makes sense. When tasks vary, routing only the difficult cases to heavier models keeps the system efficient and responsive. We must also consider the resource demands during runtime. Longer input contexts, growing caches, and additional reasoning steps increase latency and memory use. A model that looks good alone may become costly when handling long sequences or multiple tool calls. Throughput depends on the model, the input length, and how often inference repeats. Architecture review should check if the model remains affordable in the actual operating conditions, not just if it is accurate enough. The next step is to determine customization needs. If the task is stable and well-defined, lightweight tuning methods like PFT, LoRa, or adapters simplify customization. For memory efficiency or large-scale deployment, quantization and optimization tools become important. If deployment control is critical, open or hybrid models may be preferred despite operational complexity. The best choice balances the minimal techniques required to meet behavior, speed, and governance requirements. Finally, the architecture must be explainable. The team should clearly justify why each model fits its role, why that role has a certain thinking budget, and how the deployment meets organizational constraints. A transparent design makes the division of labor and trade-offs obvious. This clarity is crucial because architectures evolve, and future changes are safer when the original reasoning is easy to understand and defend. This part focuses on how an agent moves from generating ideas to actually taking actions. It covers the challenges of controlling what the agent can do and ensuring those actions are safe and reliable. Once the model is selected, the focus shifts from what it can think to what it is permitted to do. The system must cross from inference into action, which involves managing tool use and controlling outputs carefully. This ensures the agent not only generates good ideas, but also acts in a way that is safe and predictable. Designing the agent now involves specifying how it interacts with tools, how its outputs are checked, and how its actions are governed to keep the system predictable. The model choice forms the foundation, but the main challenge is enabling the agent to act safely and consistently within its environment.